looking back at faint objects or to do high time resolution, because you've got enough flux that you can, instead of integrating for minutes or longer, we can do like 10 Hertz observations in some cases for certain types of objects. And of course, as I say, the next big thing is the Rubin Observatory. And I think it's worth just emphasizing what a huge impact this facility will have when it comes online, hopefully towards the end of the year. And progress has been amazing over the last year or so. Just recently, the M2 mirror was installed, and so I think we are going to hear about this from Jelko, the project scientist, on one of the last talks today. And of course, it's really going to do an amazing thing. It's going to cover 18,000 square degrees of sky, which is what I call a wide, fast, deep survey. And you can see the footprint of that survey in the bottom right diagram there. Typically, there'll be something like 800 to 1,000 observations of any point in the sky over the 10 years of the survey. So a huge resource in terms of time variability of the universe, and down to magnitudes unprecedented. What we expect is of order 10 to the 7 alerts a night. Now, that is a sort of mammoth number, and one thinks, well, you know, in the scheme of things, what we've been doing so far in following up alerts has been manageable, because the biggest survey, which has also been a large producer of transients to date, has been the Zwicky transient facility, but this is orders of magnitude more. And some people sort of throw their arms up in horror, because the idea of like, well, how can you possibly deal with that? And so this is where machine learning, artificial intelligence comes in, and this will help us solve the problem. Not that we could even consider, for example, doing spectroscopic classification of objects down at like 27, 26, 25. Even with SALT, you know, we don't get much further, much fainter than about 22 if we're lucky. So the program that we've been executing is sort of helping us in our decision-making process about what things are important. You know, we can't possibly follow up all of the thousands of, say, dwarf novae cataclysmic variables that are a dime a dozen. You know, we don't want to focus on things like that. We want to look at the interesting stuff. And sometimes that interesting stuff will come out through anomaly machine learning, looking for unusual types of phenomena that perhaps we've never seen before. So one of the big projects, which is being led by my colleague Steve Potter at the SAO, and this was mentioned also in talks yesterday, is South Africa, the SAO's Intelligent Observatory Project, which, you know, has been going now for several years. And it started in a really relatively modest idea of being able to network our telescopes at Sutherland to enable within this network. And there's a poster on it by Steve in this session. But this picture at the bottom just shows you the huge number of facilities. And Ros Skelton in her talk yesterday showed all of these facilities, but this picture's already out of date. It's missing 3 telescopes that have just sprung up in like the last year or two. And one of the really important ones is the new prime wide field infrared telescope, 1.8 meter, 1.5 square degree field of view, using the Roman observatory detectors to do wide field infrared observations, and that will be a major facility that will help in our study of transients. So not only are we dealing with the telescopes we own ourselves, but our intention is for those facilities that we host from other countries, that they will come on board with the idea of putting some of their time into this sort of transient follow-up facility. And so that is our aspiration. And as you'll hear in a moment, that this has been working quite successfully. And I see my slides are not advancing. Is there a glitch there? Oh, okay. So here's a nice picture to show some of those facilities, and I'm not going to dwell on this slide because I think Roz overviewed all of this before. But these are some of the facilities that we're hoping that will become involved in this follow-up program. And, you know, obviously missing from this slide because it's only just been built is the Prime Infrared Telescope. And so what is it all about? So this is something that Steve and his colleagues helped produce this slide that's showing what is the vision of this. And so the idea is to have all of these telescopes integrated into the so-called intelligent observatory, coordinating follow-up using intelligence, built-in intelligence. So making sure that we cover all our bases in terms of, like, depending on the type of transient you're wanting to follow up or variable object you want to follow up, targeting it with the appropriate sort of observation. Is it a low resolution spectrum just to classify it? Is it high-speed photometry because we know it's probably a highly variable object? And so this is enhancing, you know, our research capability both within the country, but as you'll hear later when I talk about the global expansion of this, hopefully into international partnerships as well. And at SAO, this is like a really important mandate is how will we operate in the area of the fourth industrial revolution. So this grand idea of turning the Sutherland Plateau into this AI transient follow-up machine. So I'm not going to go through all these other bullet points that go about, you know, what are the things that we're going to do to service our community and our users. And I'm talking about not just the users in South Africa, because we give a significant amount of time on our facilities to overseas observers as well. And now it's even the case that they don't even need to come here necessarily because of the remote observing capabilities. And so we're moving away from the traditional way that we used to allocate telescope time, namely an astronomer would get a week, they'd go up to Sutherland, they'd do their observing, and that's the end of it. That's not an efficient way to operate in the 21st century. So we're moving to Q-scheduled automatic observations or remotely operated observations, or observations with teams of people like transient interest people. There's a few of us who are leading different programs, Paul Crute, Steve Potter, myself, Patrick Vogt, and our cohorts of students and postdocs. And they do the remote observing for a grander program, not their own targets necessarily, but that certainly includes them as well. So what we have to do is, of course, interact with the alert brokers, and the obvious ones are like the GCN alerts for things of like gamma ray bursts, gravitational wave events, those sort of things, and also have the automatic scheduling software. So we've been working a lot with the LCO, Las Cumbres Observatory, who've developed all this software for their network on TOMS and something called AONS as well. And we've used the OCS systems that LCO have built for our own telescopes. So here's the current status. We have 3 telescopes that are involved so far in this work, in the sense that we're actually doing observations with these 3 telescopes. And we can now put things into an automatic queue for the 1 meter Lasady telescope. So this is like no human intervention once it's in the queue. And this is just an example that we can now do remote observing. Initially, we said, well, we'll just do it from Cape Town, but now it's going to be, you can do it from overseas. And so, yeah, that's really what is happening with the IO. And the way that we managed to do this is using these sort of softwares that allow integration of facilities. But I'm now going to move on to the future. And the first one is the BRICS Intelligent Telescope and Data Network. This is a program that grew out of a flagship call several years ago, and it's become quite a large program with the idea of harnessing existing telescopes in our BRICS countries with the idea that we would be servicing the next big data producers on the planet. And that's obviously what I've already talked about, Rubin, but also the SKA. And so the facilities we're talking about are in the optical, sort of summarized in this slide for different countries. You might wonder about Gemini, but Brazil has access, a partner in Gemini and a partner in SOAR as well. So it's not just our own facilities, but it's facilities that we have access to. And in the radio, of course, well, we don't need to talk about Meerkat and the SKA coming in the future. So then I'm going to finish now with the next project, which sort of was a spin-off of the BRICS project. And this is the African Integrated Observation Network that Miana spoke about yesterday. And this is doing essentially the same thing, expanding the Intelligent Observatory into bring other observatories, existing observatories like the Euclidean Observatory in Morocco, like the observatory in Egypt, Cotomea, also the Entoto Observatory, and the future possibilities as well. So in these cases, it's like Cotomea. It's an ancient 1.9 meter telescope, about the same vintage as the one we have in Sutherland, but with a wonderful instrument, which is a huge asset. And we heard yesterday about future projects in Egypt with a new observatory to be built in the Sinai, which would be fantastic. And I really, Yosri, I really wish you well in that project. In Toto, we've heard there's 2 1-meter telescopes, well instrumented, capable of doing great science. There are challenges there. I'm not going to go into them, but that's a huge possibility. Then there's the Oka-Medan Observatory, which I had the pleasure to visit at the African Astronomical Society annual meeting in Morocco in April. Again, a wonderful site, already with robotic facilities. So they're already geared up to do this type of observations. And the most recent initiative is a small one that I've been involved in, and that's to bring back a telescope that's been mothballed for over a decade. And this is really through the good offices of Charles Magruder, who I had this idea to let's bring this telescope back from the dead. And so this is a wide field GRB follow-up telescope. And just in May, a team of us went up there, installed a new camera, got first or second light, and we hope to have this facility up and running by the end of October. And then, so what's the reason for this? Well, it's driving, of course, collaboration through Africa. That's the theme of this IAU, actually, is how do we expand? How do we support research in Africa? How do we develop the talent, human capacity development? How can we become a player on the world stage? And I think through this will be a huge possibility. And with that, I will end. Thank you.
Great talk, David. Thank you so much. So I think we have like few minutes, maybe 3 minutes, 4 minutes for questions. So, okay, Bonaventure, yes. Josephine, thank you.
Thank you for that wonderful presentation. I just want to ask a question based on your last statement. What can you do in terms of human capacity development? Some of us are involved in that human capacity development, and we run these summer schools, and we feel some of these students can have access to some of these telescopes to learn how to observe and do data reduction. We want to do with LCO. Now, what are your plans to help such programs? Probably wherever we're having such summer schools, we could have remote access to the telescopes. What could be the procedures and what is the possibility?
It's a good question, Bonaventure. And so, the African Astronomical Society, which sort of was restarted in the last few years, has as one of its mandates just what you said. So I've been talking about the technical aspects of networking telescopes, actually being able to have the capability to do remote observing, do robotic observing. Of course, that will mean that anyone in Africa, they don't have to travel anywhere. They can do this over the internet. maybe a decade or more ago, there were big challenges in Africa with internet connectivity and bandwidth, and many of those have improved, hugely. And so we're now at the point where we can do this sort of thing. But there's a sort of group within the AFAS, and I think Mayana and others here who are part of AFAS know about this, and we have this as a mandate to be able to get students and young researchers access. And we heard yesterday from Inkani regarding the SALT telescope that time is available on that telescope. And so the resources are opening up, the facility coming available. And so I think it's a very promising future, but it needs obviously coordinated activity. And it's one of the things on the monthly agenda items of the meetings that I'm part of, the Science Committee of AFAS, but also the other committees, education and outreach committees as well.
Great, thank you. One more quick question answer, yes.
Taking data from various observatories is one thing, but I'm curious how you plan to combine the data together.
Yeah, that's a good question. And to be honest, I don't have an immediate answer for you other than the fact that, within the observatory at SAIO, we have a means of distributing the data very rapidly. I think you, Inkani, made the emphasis that typically the data is available the following day from SALT, and likewise the data becomes available also from the smaller telescopes. I think we will need to streamline the access to data because at the moment it's on servers that we have, accounts on to go and extract the data. This is probably a question to Steve about how we expand that into a more accessible through, collaboration and also a secure system, right? So we don't want to run into problems that some other facilities have had recently. So, yeah. But it is a good question. Yeah.
I think we will have to continue. Thank you so much, David, once again. I think David will be here the all 2 weeks, so please get in touch with him. The next speaker is Judith Provençal from US, from the Mount Cuba Astronomical Observatory. And she will be speaking about the Whole Earth Telescope and stellar seismology. So Judith, just wait, just that we get presentation. Okay, so now we can go, no? Okay, perfect. I will let you know when 3 minutes are left.
Okay, thank you. And thank you for, I'm very excited to be here. This is my first time visiting Africa. And so it's been an interesting journey already. But I'm here today to talk to you a little bit about the Whole Earth Telescope. And some of you, let's see, how does this work? There we go. What is the Whole Earth Telescope? Well, the Whole Earth Telescope is actually an international collaboration of observatories around the globe. And our goal is to obtain uninterrupted data, high-speed photometry of variable stars. And this is a ground-based collaboration. And the reason we have so, well, before I get into details, I have to lay a little bit of groundwork about how the high-speed photometry works. Oops, I went backwards. Green button, got it. This green button.
This is forward.
Okay. Got it. Okay, got it. Okay, so I'm going to tell you a little bit about how photometry works. Talk about light curves, Fourier transforms, and then what is astroseismology, which is we are trying to use the pulsations of these stars to learn about their interiors. So photometry and light curves. This is the little bit about David was talking about, high-speed photometry and the realm of time domain astronomy. So what we do on the left here is a picture of a field of stars with one variable star, which is labeled with the little blue dot. It doesn't look special. You can't really tell looking at it that it's a variable star. But what we do is we take thousands of pictures of this thing and you draw a little circle around the star. You extract the brightness from the star. And every point in this plot over on the right is from an individual image of the star. So this is a light curve on the right-hand side, and you can easily see the pulsations of the star. And this is a white dwarf star. It's one of my favorite stars. It's fairly bright for a white dwarf, so This is a pretty nice little light curve. So how do we get from light curves to information that we can use to build models of stars? So what we need is actually the frequencies of the stars. So the tool is the Fourier transform. So you feed the light curve to the Fourier transform and you get out a list of frequencies. Now, this is the reason why we need a whole network of telescopes. This is data from a single site that has observed for, I think this one was about 6 nights of continuous data. So when you're at a single site with a single telescope, the sun rises every morning. You have to stop observing. And that gives you gaps in the data. So this is the pattern that you get from a single sine wave sampled exactly as your data that includes gaps. And so even though there's only one real frequency in there, you get a forest of frequencies in your Fourier transform because of the gaps. And this is a problem when you have a complicated star like the one I was just showing you. GD358 is a pulsating white dwarf with multiple periodicities that are present at the same time. So when you have a nasty window, which is at the bottom panel here, that's the pattern that you get from a single sine wave sampled exactly as your data. So when you're trying to pick out from the top panel what frequencies are real and what are aliases, it's impossible to do that. And so what we try to do is have a whole series of friends around the planet, and we set up observing campaigns, and you pass the star off to the next friend. So let's say I'm starting off in Delaware, which is on the east coast of the United States there. I'm observing, and I pass the star off to someone in Texas, someone in Hawaii, someone around to, let's say, New Zealand or Australia. And then we've used David Buckley has been observing for us before, South Africa, and then over to Brazil. So you try to keep the thing going so that you get 24-hour coverage. And this is one of our light curves where we had a variety of telescopes. I forgot how many for this run, but each color is a different observatory, and you combine all the data together to create a light curve that is much more continuous. Now, this one is not continuously continuous. There are gaps, but if you look through every panel is a day. Oops, I went back, wrong one. Every panel is a day in here. If you collapse it down, at some point during a 24-hour period, someone observed in that. And so the alias patterns get greatly reduced, and then you can actually pick out the frequencies that are real. And so this would be the Fourier transform from that run. And now you can actually see with a lot more clarity what is going on in this star and how many frequencies there are. So why are the frequencies important? The frequencies are what the theorists want. I'm an observer. I'm definitely not a theorist. But the frequencies are what the theorists want to build an internal model of the star. So I want you to imagine that you have a bell and you ring it. It makes a certain tone. The stars do the same thing. They pulsate depending on what their interior structure is, what their interior composition is. So by assembling the frequencies of the variable stars, you can learn things like the stellar mass, the rotation rate, the interior composition, any structuring and layering that's in there. You can get information about that too. You can also get a little bit of information about magnetic fields. Although magnetic fields is my favorite thing to say. If there's something going on in the star that I don't understand, I can say it's the magnetic field and nobody can argue with me. So this is, again, my favorite star, GD358. We've been observing it for many, many years now. And what this is showing you is all of the frequencies that we've detected over all of the years that we've been observing it. So the color bar on the right there is the year. And then on the bottom, you've got the periods that we've observed and then the amplitudes. So this is the information that the theorists want to go ahead and then build a model of the star. And the more frequencies you have, the better. So the Whole Earth Telescope has been around for a while. It was founded way back in 1986 by my thesis advisors, actually, and David Buckley's been involved for quite a while. And then Dara O'Donoghue was also from South Africa, was a founding member of the Whole Earth Telescope. And our goal is to get continuous coverage of these individual stars to determine their frequencies. And then the scientific goal is to construct accurate models of the stars themselves. So the Whole Earth Telescope kind of differs a little bit from a lot of international collaborations in that we have a headquarters. So we ask the observers every night to upload their data to the headquarters. We reduce it in real time, and then we can make decisions about whether we have enough data on a particular target or not. So we can switch back and forth between multiple targets. So this is some of the people back at Mount Cuba Observatory when we had our headquarters there a few years ago. And we had representatives coming to the headquarters from many different countries. And then we also have a web page that keeps all the observers informed about what's going on during the run. And these runs can last anywhere from a week to one time we had one that was 6 weeks long. That wasn't continuous coverage all the time, but we were observing for about 6 weeks. And then these are some of the sites that we've used in the past. There's Mount Cuba is up there, one of my students up there in the left corner. There's a picture, there's a story behind the McDonald Observatory is the snow-covered one. And there's a story behind that, and I'll tell you, if we have time, I'll tell you about it. We got South Africa. The bottom picture here is an amateur observatory in Texas. So we actually involve a lot of amateurs in our observations as well. And then this is some pictures. This is our latest meeting back in, I think that was 2019, right before COVID hit, when we got together to have some of our collaborators. Peak Terskal is another observatory, the snow-covered one over there. And now I want to finish by telling you a little bit about a run we're planning in 2025. Our target star is G2938. And it's a pulsating white dwarf, but it's a special pulsating white dwarf because it has a planetary debris disk around it. And what we saw, let's see if it's coming up, a few years ago, we had a small run on this object involving some optical telescopes and also the IRTF, an infrared telescope. The pulsation periods for this star are between 300 and 1,000 seconds. And we saw something kind of interesting when we started to look at the infrared data. So up at the top, where it's labeled optical, those are the frequencies that GD358 was, G2938 was pulsating at during the run with the optical telescopes. And then the rest of the panels are infrared with the red numbers are the wavelength, the central wavelengths for the particular panels. So for a white dwarf, as it pulsates, because a white dwarf is a hot star, and as you look at it in longer and longer wavelengths, you should see the pulsation amplitudes go down. And at the beginning, that's kind of what you see. The amplitudes of the pulsations decrease until you start to get out to about 1.7 microns, 2 microns. All of a sudden, this stuff it starts to appear. It gets higher amplitude in the infrared. The infrared data itself is not great. We only had like 2 half nights that was decent. And so it's very hard to resolve, to pick out the frequencies that are present there. But it seems like the disk itself is reprocessing the pulsations somehow. And so we're trying to figure out exactly how that works. And so our goal, yeah, we're planning to have a multi-site observing campaign on this star next fall. And we want to use the pulsations to try to probe the structure of the planetary, of the debris disk and learn something about the nature of the original planetary system. And so we're always happy to have anyone who would like to participate. And so that's the graduate student who is the PI for this project. You can email him, you can email me, and we can talk about participation. So I think that's it. Oh, yes. What do you need if you want to participate? Just pretty much access to a telescope and have a good camera. And we ideally like a red cutoff filter, but we can get away if you don't have one, it's fine too. So if anybody wants to participate, go ahead and send us some email and let me know. So that's it. Thank you.
Great. Thank you very much, Judy. That was the perfect timing. So we have time for questions. Any question for Judy? Yes, please.
Hi there. How do you decide on targets? So who makes the decision what campaign you do?
The Whole Earth Telescope's pretty much been an informal process over the years. Someone will just while I've been running it, someone just emails me and says, hey, I have this good target. And then I talk to it with a few other talk about it with some other collaborators and we decide if it's a good idea. And usually yeah. So it's pretty informal.
Yes, Charles. Okay, Charles, then Adamajit, yeah.
I think you're at McDonald, if I understand correctly.
Yes.
Okay, so David talked about a ROTC telescope in Namibia. There
Mhm.
was one in McDonald. What happened to it?
Oh God, I don't know actually. I haven't been to McDonald in years. Because I was a graduate student at the University of Texas like 30 years ago, but
Okay,
so I don't really know.
all right.
Thank you. And then Adamajit, yeah.
Thank you. I wonder what is the terms to join your network? And my second question is about, do you need some spectroscopy data? Because actually in Morocco, we lead a large campaign of variable star. So yeah.
Actually, for this target, yes, we would like some spectroscopy as well. We're trying to do that. But I didn't hear the first part of your question.
What is the term to join your network? So to have the red point in the map.
To have a red point. Well, in the past, people just express interest, and then we join. People join. As far as the collaboration, our usual. Everybody gets included in the papers that come out of this. And so the usual thing is, even if you don't get data, if you apply for data and you observe and it's cloudy, you still are on the paper. As far as being just joining the collaboration, it's as long as you have a telescope and a camera, we're happy to have you. The more the merrier for us, because we're dependent on the weather too. So I don't know if that map is still up there, but Europe has there's 10 little red dots in Europe. There was one run where the whole continent of Europe was cloudy. So the more different telescopes we have at different longitudes, the better it is for us in different latitudes.
Okay, great. I think we can go to the next presentation in the meantime. Thank you, Judith, very much. Let us thank Judith once again. Actually, just a quick notice from the Astronomy in Africa survey that we did. Actually, we saw that the community for the transients across Africa is still quite small. Except South Africa, the other countries don't participate much. So it's a good opportunity that that really more countries join. Okay, good. So now the next speaker is Grazina Tautvasiene. If I don't pronounce your name well, please feel free just to do it properly. I apologize for that. So Grazina is from Lithuania, from Vilnius University, and she will be speaking about our Europlanet, the Europlanet Telescope Network for promoting international collaboration. Thank you.
Thank you. You pronounced my name very well, which is quite rare. So I came here to promote the Europlanet Telescope Network. And this telescope network was established while implementing the European Commission funded project. We started in 2020 and just finished at the end of July. This project was proposed in order to provide free access not just to the telescopes, but also we provided access to planetary field analogs, and one of such places is in Botswana, and also there are quite many laboratories to which we provided access, the virtual observatory, space weather services, geological mapping, machine learning, and of course, the Europlanet Telescope Network. We had 50 beneficiary institutions from 24 countries in Europe and around the world, with further 44 affiliated partners. So the Europlanet Telescope Network currently unites 17 observatories with 25 telescopes in 12 countries, and the Falkless Telescope Network with 21 telescopes. So mainly the telescopes are located in Europe, as you see. However, several telescopes which belong to this Falkless Telescope Network are located in other countries, one in Africa. So now we already ended our project, and we would like again to how to say, make some steps to widen this Europlanet Telescope network, and we kindly invite observatories from Africa to join to become more visible in Europe, especially if you have interest in collaborations dedicated to planetary research, but also other fields of astronomy also will be covered by this network. So here is the link to the table which provides the full information about available facilities, how it is possible to apply for observing time, what is instrumentation, what size of telescopes. Telescopes are from about a half of meter to 2 meters. There are several telescopes of 2 meters. So here in Africa, you have 5 2-meter class telescopes, so they are very welcome to join this network. And I noticed about 10 smaller telescopes, so you indeed are very welcome to join this network. So in this table, it is possible to find information about a possibility of service observations, remote observations available, about possibility of collaborative projects, accommodation possibilities, contact persons, everything what observer needs to know. I myself an observer, so we collected everything what could be useful for observations. So during the project period, we had, of course, this pandemic period in the middle. So from the funding of the European Commission, we granted free observation time of 259, and observers from 11 countries were awarded the observing time. They came from Brazil, Germany, Greece, Iran, Italy, Lithuania, Malta, Poland, Russia before the war, Spain, United Kingdom, and we are glad that we did not make that for purpose, but gender among principal investigations was quite equal, 20 females and 23 males. And there were senior researchers, early career researchers, students, and even amateurs. We're glad to give access to amateurs to professional telescopes and to raise qualifications. So main applications were to observe asteroids, comets, exoplanets, planetary systems, and some other topics like Gaia alerts and so on. So during the three years observations, we are glad that there were 19 papers published in refereed journals and more in preparation. So even with quite small telescopes, it is important to observe, and there are valuable results. And what kind of observations we are doing? So exoplanet transit observations, follow-up observations for space missions. Nowadays, there are quite important space missions dedicated to exoplanet research, like Gaia, TESS, Plato is in preparation, Ariel. So here are examples of transits observed on different telescopes. Also, chemical composition of planet hosting stars, how distribution and planetary, what planets form, what are characteristics of stars, like metallicity, age, temperature, how such formation depends on stellar characteristics. And we are glad that we have also in our network spectroscopic instruments, not just photometry, like in some other networks. Here are examples of amateur observers, what they made. There is such a website, ExoClock, and here the results for the Ariel space missions mainly are collected. Also, we provided some tools which could be useful not just to our network, but to all observatories. There is such a Gaia Ga website where it is possible to find for which asteroids observations are most important, and also what forthcoming observations would be useful. And it is possible to find useful targets. And what is interesting in the asteroid research field, that not just search for asteroids is going on, but also observations of light curves and determination of asteroid shapes is on a way. So there is another tool, PVOL, Planetary Virtual Observatory and Laboratory, where we announce such companies of observations of solar system planets like Saturn polar storm, Jupiter storm, and Venus atmosphere features can be observed. So in this telescope network, we had two science workshops in 2022 and 23. And during the first workshop, we had participants from 43 countries, and they were early career researchers, 63, 40 amateurs, 80 amateurs, 43 senior researchers, in total 21 participants. So we were organizing summer schools, and we will try to continue this activity. So in 2021, during pandemic, we also organized a summer school with 40 participants from 33 countries and used remote observations from the Molėtai Astronomical Observatory in Lithuania. So here are places from where participants came. Just one from Africa. We hope you will know more about our activities and more people will come. For asteroid research training, we had a recently workshop in Estonia with 19 on place and 23 remote participants, and also a summer school. We have a series already, summer schools dedicated to ground-based observations for science, space missions and science communication. Here is one was held in 2023 at the Molėtai Astronomical Observatory. Here you can see my telescope. And we had a workshop for comet observers in Prague. Also, now when the project is ending, we take care about the sustainability of this, and there is now a Europlanet Association established, and it will take care about this network. So at the moment we have 10 observatories which will provide free of charge observing time for collaborative projects, and the Falklands network of telescopes is providing free of charge time for educational projects. So you are welcome to use opportunity to collaborate, to join collaborations and use free of charge time. Observatories which wish to receive payment for their time also are in this network, and prices are provided. No need to search. So thank you for your attention, and let's collaborate.
Great, thank you very much, Brezina. So very nice talk. And we can go to the next one, please. Very nice talk. We have a time for very, very quick question and quick answer. Yes, Zuhair.
I am Zuhair Belkhaldoun from Okeimdan Observatory. I will talk about the observatory in the next session, I assume. And we will be happy to join Europlanet network. So keep in touch for that.
Very happy, very good. Others are also welcome.
Good. Let us thank Grazina once again. It would be great, really, that the collaboration comes out from this. So the next talk will be given by Przemysław Mikolajczyk.
Yeah.
And from Poland, from Nicholas Copernicus University in Torun, and with the topic of black hole TOM, an automatic tool for photometric time domain data. Thank you.
Yeah, thank you for having me. This is not the presentation.
I have it here as a presentation.
This is my poster from Friday next week.
But you do have 15 minutes.
I do, but this is not the presentation.
Oh, sorry. So you mean okay, yeah. You uploaded the talk.
I did.
You did. Okay, let us give the maybe to make it faster. Can you come? Let us check.
Oh, sure, yeah. Yeah. Yeah, so hello everybody. I'm Przemek Mikołajczyk from University of Warsaw and from University of Wrocław, Poland. And this is my pleasure to present to you Black Hole Tom. So thank you first foremost for the organizers and scientific committee to award me this talk. And so I will show you that our team consists of many people. I'm just one of 3 people who right now are employed through the Opticon Radionet Pilot grant to work on this issue, to this matter. And Łukasz Wyrzykowski from Warsaw is the PI of the project. But we also collaborate with people from many different countries. So let's imagine that we have a telescope somewhere, located somewhere in the world, and especially in places like Europe, where we don't have a lot of great weather, sometimes we ask ourselves a question: what can we use this telescope for? If we have only, let's say, a dozen or 2 dozen clear nights a year, it doesn't really make sense to continue doing science in such a place. So maybe it's better to just sell the telescope and clear the forest. But let's say that there is a transient supernova in one of the galaxies, and the user of our service says to the BH Tom, to the Black Hole Tom, observe it now. So there are many telescopes in the world. How can I access one of them? Sometimes there is no way to apply for telescope time, or the proposal page is in language that we don't really know. There is a horrible weather pattern, so why even bother to try to apply for such a time? Do I have to go to observe myself, or maybe somebody can do the observations for me? And finally, how to process the data from all the different telescopes around the world. So here comes the other questions, that the other problems that sometimes arise when observing a target. Sometimes we need a long-term observations, and nobody is going to award us a year-long a whole telescope for 1 year to observe one particular target. Sometimes we don't have access to the telescope which is located in a place that can see our target. We don't have time to process images from all the telescopes located all around the world, different cameras, different observing modes, different calibration patterns. We just don't have time to do this. And of course, in the final stages of such a project, we would like to write a scientific paper, which also takes a lot of time to prepare. So what we established is a network of telescopes, and it began, right now it is founded by Opticon Radionet Pilot grant, and it ends in the February of next year. It not only consists of these telescopes located all around the world, but it's also dedicated for the transnational access to optical and radio telescopes. It's aimed to train a new generation of astronomers via schools and workshops. And it provides a lot of other services like access to archival data. So the whole project started, is a part of Opticon since 2013, and the precursor of the Black Hole Tom was Cambridge Photometric Calibration Server, which was dedicated to for standardization of your photometric observations. So it was only designed to take different photometric measurements from different telescopes and to standardize them to standard magnitudes. And after a decade, now the whole project consists of over 100 telescopes, not only small telescopes, because the biggest ones in our network are over 2 meters in diameter. And the whole BH-TOM portal started operations in the early 2020 and was developed basically during the pandemic time. Right now, we have thousands and thousands of observations submitted to us every week. We can process them, let's say, in real time. So this is the European part and Northern African part of the network. It kind of overlaps with the network of Europlanet, which Grażyna showed a while ago. But also we have a lot of telescopes located somewhere else in the world, spanning from Australia, Northern and South America, and also in Africa. But in Africa, we have a huge gap because we only have telescopes here in Seio. I think it's Lesedi telescope, LCO node here in South Africa, and also Kotamia Observatory in Egypt. So we would really like to invite you guys to register your observatories in our system and also to take part in this project. So what is the BH-TOM? What is BH-TOM and what can it do? So basically, Black Hole TOM is a web tool. A web tool when you can go and register yourself as an observer, as a scientist, as a student, when you can register your observatory, your telescope, your instrument, and then simply put a target into a list of targets. And then this target can be observed for everybody who has a telescope in our network. You just specify the target name, you specify the, let's say, event class, you specify the cadence, you specify the observing conditions that you want to have this measurements taken, like filters and so on and so on. And the whole thing works in automated fashion. So you don't really have to take care about the observations after you put your target into the list. People all around the world will observe for you, and they will upload data straight to the service. They will not do the reducing the photometry themselves. They will just put the file into the web page, and our standardized, our automated pipeline will do the photometry for you in the same matter for every single file that is uploaded, and then it will create and display for you a light curve that you can analyze later. Also, BH-TOM has already built in the archival data, which are being queried after you just create your target. So when you create your target, all the archival data that is displayed here is being downloaded. So you have everything in one place. So you have your own follow-up observations, as well as all the archival data that is available at the time on the internet. We have things like Swiki Transient Factory, of course, Gaia, and Atlas, I think, is already there because there were some problems in implementing this, but there are many more archival data. Also, this very, very old archival data, like Dash project, which also will be available in BH-TOM very short time. So after you upload your images, after many people upload their images, we are being left with science-ready light curves that then can be analyzed, and then we can write papers using this data. So as you can see, all these photometric points that you can see in the plots are the plot is being created from different observatories, from different instruments, and it all happens in automated fully automatic matter. So how does it work in reality? So the whole thing is designed for alerts, but of course you can propose a your own science case, which doesn't have to be a transient. It can be a variable star or anything else. But the whole thing was designed around Gaia alerts, science alerts. So when we have a survey that is alerting something, the brokers are informing users that there is a need for observation. So there is a supernova, let's say M81, and let's observe now, or let's observe some other event. Then these users are putting the observing request to our service. So they basically are registering a new target. Then this target is sending requests to many different telescopes all around the world. And these telescopes, after gathering the data, are uploading the data to our system, which is being then reduced. At the same time, archives are being queried. So to have a full image, full light curve for information about this target that is available at the time. And there is this crucial point here. So the data reduction, instead of uploading a already reduced photometry or a file with reduced magnitudes, we have this data reduction step. And we are handling it ourselves. So all the information, all the images are reduced exactly at the same manner. And we are also taking measurements for all the stars in the field of view. So not only for your target, but at the same time, we are building a huge archive for all the other targets that are visible in the fields of views of the desired targets. And after this, of course, the scientific papers, scientific publications can be written. In the future, we would like to substitute the humans with computers. So the computers can communicate themselves, and humans don't really have to do anything. So if you have a robotized telescope, then the information can be queried from our system, and the robotized telescopes can do the observations, upload the data, and we do the rest. Many different science cases are present in our system. Of course, you are welcome to propose one of your own. And number of publications have already been published, and many more are in preparation right now. Of course, there is an API right now, so you can access our service without the need of this tedious task of logging into the web page. You can just script it out and use it via terminal. And every week we are sending out a newsletter of the targets which are interesting. Of course, you can also get a newsletter which is suitable exactly for your observatory, which is with the targets which are visible from your observatory, which are visible with your telescope. And so to summarize, why use BHTOM? Because of the various science cases, access to multiple telescopes right now, close to 100 telescopes around the world. Telescopes come in all sizes, so you can observe bright targets and very dim. The automatic querying of archival data, so you don't have to spend the time to look for it yourself. And the automatic reduction, automatic measurements, photometric data reduction makes the science light curves very coherent. It's perfect for education and outreach, because if you have classes and you're observing, you can just put your file right away into the system, and you can see the photometric point in seconds sometimes. And it's very easy to use, and it will always be a free platform. Every year since 2010, we've been organizing workshops, and this year it's going to be a 15th in Crete. So all of you and all around the world are welcome to join us and at the end of September, at the beginning of October. So please enjoy BHTOM, register your telescope, and be a part of our project. Thank you very much.
Thank you very much. Very nice talk. Questions? In the meantime, the technical team, maybe you can go to the next one. Yeah, the next one. Yeah, yes, go ahead.
Okay, thank you very much for your presentation. I want to ask about the requirements to be in your network, and what is the benefits we can get from joining your network?
Yeah, so there are no requirements as long as you are a part of, as long as you have a telescope and you're willing to allocate some of your time for observing our targets, and maybe you want to have your target observed by someone else, you just register and you register yourself. We allow you to use the platform right away. And if you register your telescopes, after 48 hours, we are checking that all works and you can upload your images. So basically you can do your photometry, even your photometry, you can do with our platform. And the upside is obvious one, because you are, even if you put 1 or 2 measurements into our light curve and then it's published, you are an author. So we have very straightforward publication co-authorship policy. So basically, if you have a telescope that isn't really doing a lot of scientific output, you don't have a lot of observing nights, and you want to justify existence of such a telescope, even for teaching purposes or for outreach, you can do, let's say, 10 nights a year of such observations, and you can be co-author of 5 papers.
Thank you.
Good. Thank you very much. Unfortunately, we have
Thank
to
you.
proceed. Thank you very much, President once again. So the next talk will be given by Bruce Bierman from Caltech in US, and Bruce will be speaking about the benefits of the virtual observatory. Can we please go to the next? Yes. The benefits of the virtual observatory to underserved communities. Is Bruce?
Okay, I presume you're simply.
My name is Bruce Berriman. I work at Caltech in Pasadena. I'm the NASA representative on the IVOA Executive Committee. I'm the chair of the IAU Functional Working Group on the Virtual Observatory, and also I'm the IAU representative to CODATA. All right, the first question I want to answer is, what is the VO? The most succinct description I know of has been provided by my colleague Pepe Fabiano at CFA, a multi-wavelength digital sky that can be searched, visualized, and analyzed in new and innovative ways. It's essentially an ecosystem of interoperating tools and services deployed by worldwide data centers, rather than being an actual archive itself. VO is built on open access and discovery protocols that form the plumbing. Now, the protocols themselves are developed by the International Virtual Observatory Alliance. It was founded in 2002 at a meeting in Garching in Germany, and you can still find the proceedings from that meeting online at Amazon. Now, its overall mission, as stated in the book in 2002, and it's still the same today, is to facilitate the international coordination and collaboration necessary for the development and deployment of astronomical archives as an integrated and interoperating virtual observatory. Its goal is to make data sets discoverable and accessible to everyone. Inclusivity is a central theme of the VO. Institutional membership is open to all nationally funded VO projects and international organizations who seek funding from their national agencies. The IVO itself has no central funding. Membership's grown from 3 founding members in 2002 to 24 in 2024. The newest members are the SKAO and the Kazakhstan VO. These 2 members are excellent examples of the diversity of organizations within the IVOA. One is a huge radio telescope, the other is a very active virtual observatory in a developing country. There's also been an expression of interest from the Jordanian VO. So more on the Kazakhstan VO. They've been busy making their archival observations VO accessible, including data acquired at the robotic telescopes located at the high-altitude Asi-Tugen Plateau, which you can see in this picture on the top left, as well as many archival photographic data sets. Many of these data will be valuable in studying the long-term time history of many astrophysical sources, and they're providing a valuable service to astronomy. So how does the IVOA go about doing business? Briefly, work focuses on semi-annual hybrid interoperability workshops that are open to all. You don't have to be a resident in one of the member countries. Anyone can take part. The member countries have seats on the exec committee and vote for the leadership of various groups, but anyone can actually join into the meeting. One meeting is in the northern spring of each year and the other is in the northern fall, usually consecutive with the ADAS meetings. We do try to avoid registration fees as far as possible to encourage attendance. The next meeting is in Malta in November, and the previous meetings have been in Sydney, Australia in May of 2024, Tucson, Arizona in November of 2023, and Bologna, Italy in May of 2023. There is a formal process we go through for approving protocols that you can see in the chart on the right-hand side. Standards involve developing, documenting, and reviewing through a formal process. The standards are developed by working groups, coordinated by a technical working group. A committee for science priorities recommends science drivers to the executive committee, and the whole organization is seen by the executive committee itself. Now our vision for the IVOA is ultimately to enable new science by engaging the international community to ensure that data are sustainable and accessible, and ensuring that data are in line with FAIR principles. Let me briefly describe FAIR principles, since it's the subject of a lot of work in the international community in many disciplines. FAIR stands for findable, accessible, interoperable, and reusable. It's a set of 15 criteria that, when met, will support the mechanics of machine access to data. The IVO has already made considerable progress in FAIR principles, and you can learn more about it in this talk by Simon O'Toole that's freely available on YouTube. So I've told you about how people can take part, how we go about doing business. What about services that are available? So there are many freely available tools. No, they're open, they're accessible by any of them, by anyone. You're likely to know of many of them. Aladdin, ESA Sky, and Topcat and Firefly are shown here. They all intend to aggregate and display multiple data sets, and they are used worldwide. An example of data, or a very good example of data, is Gaia. These data are only accessible through VO protocols. The worldwide community has taken full advantage of them to publish a total of over 9,000 papers as of September 2023. And it's not just people from huge data centers, it's also people from developing countries have taken full advantage of them. Here are just 4 such papers that I found from a quick search on ADS. So let me move on to engagement with the IAU, which is central to our goals. In particular, 2 goals that are listed in the IAU plan and that I've italicized in the chart here: fostering inclusiveness and education and global development. In support of these aims, a VO working group within Division B was formed in 2021. The same year, the IVOA signed an MOU with the IAU OAD to support these aims. The agreement came about because of a joint IAU OUD project, Astronomy from Archival Data. Now, this project, which was run by Priya Hassan from Hyderabad, was extraordinarily successful and received 915 responses from all over the world, including many people from developing countries. And that's certainly something that students wanted to see happen. The project took place over 6 months remotely during the pandemic. It featured everything from live Zoom sessions and lectures, which led to students selecting projects and mentors, and then finally the students presented their projects at the end of the workshop. IVOA members were among the presenters, and VO tools, such as the ones I mentioned earlier, featured prominently in in the workshop. It released a total of 80 videos that you can all find on YouTube, freely available. I also recommend a talk by Priya Hassan entitled The VO in Education, Data Accessibility in Developing Nations and Access by Underprivileged Groups Within Developed Nations, at the Division B session entitled Community Engagement, Open Science and the Virtual Observatory, which will be held on August 12th from 10:30 to 12. Priya is an excellent speaker, and I recommend you try and listen in to her if your schedule allows it. University of Heidelberg in Germany has developed a semester-long class on using VO tools. It's been made publicly available, so you can download it and carry out all the exercises. The screenshot on the right-hand side is a screenshot from one of these exercises that you can simply go through in your own time. And it's recommended as a way to learn how to use VO tools on your own. Finally, there's going to be a satellite workshop at this General Assembly aimed at students and educators in Africa, be held on August 14th, and will emphasize a lot of hands-on tutorials for VO tools. There are many other educational resources within the VO, from summer schools, workshops, and so on. They're all posted on the IVOA education site, and you can download them and work through all the examples as well. We have fewer resources for training developers. The principal resources that document on publishing the VO. The reason this has come about is that many of the developers in data centers were actually participating in the VO from its very early days. We now recognize, though, that we have to train developers and astronomers in new communities that are not necessarily members of the VO. And so we're setting about seeking funding for such workshops on publishing in the VO that are going to be based on the VESPA VO workshops for planetary science that have been held by the Observatoire de Paris. So altogether, we invite everyone to stay connected and get involved in the IVOA. We have a feed from what is formerly known as Twitter for Facebook and Slack as well. In fact, the Slack channel features a special channel on Ask Anything You Want about the IVOA, which is useful to newcomers. We also have a newsletter that we try to publish twice a year that describes new services and science done with the VO. And the screenshot you see there in the middle is taken from one of the newsletters. So finally, I invite everyone, dive in and take part. If you're interested in learning more, please get in touch with me or any member of the IVOA executive. We'd be happy to talk to you. So thank you very much.
Great. We have time for, is Bruce connected? Because I cannot connect here. I'm having problems with Zoom. Is Bruce connected?
Yes.
Yes?
Yes. Can you hear me?
Okay, great. Hi, Bruce. Great. So we have time for one quick question and answer. Any question for Bruce? Any question? Okay. Okay, I think, yes, I think currently there are no questions, so I can just a bit highlight and ask for the trainings that you are planning to come in the future for the developers, and how people can assign for that. I mean, in particular for the developers, if we want to distribute across Africa, how people can sign for it.
That's a difficult question to answer right now because we haven't actually got funding. We'd certainly be interested in working with people from Africa. I think the very best way of doing this would be working through Division B and Division C in education and seeing how we can work something out to provide the right training. I'm not quite sure how much everyone in African observatories knows about the VO or implementation of protocols. So it's a little difficult to give a detailed answer to that question. I would hope that workshops that we are able to get funded would be virtual or hybrid so that people can join from anywhere. I mean, we very much like to see that happen. Sometimes, though, if you get funding from a particular country, they'll want preference given to people in that country and so on, which is really not the way we like to do business. We really like to involve the whole astronomical community as best we can.
Okay. Okay, great. Yes, Patricia. So Patricia is having an additional comment or question.
Hi, Bruce. Very nice description. Thank you. Just to make it clear that within the SAO and in collaboration with the South African Radio Astronomy Observatory, we have some while ago tried to establish a virtual observatory. Unfortunately, it hasn't been funded, but we're still active as far as we can do. And with the help from colleagues, particularly from the CDS in France, we are running this workshop next week, to which people from all over Africa have been invited, not just from South Africa. So we've really only got our foot in the door, but people like Bruce and others in the IVOA have been very supportive. And it has huge potential for education at every level, from school level upwards. And in terms of educating professional astronomers, it's very important that they understand these tools and they then actually get access to all the free information from everything from the James Webb Space Telescope to the Southern African Large Telescope. Thank you.
Thank you very much, Patricia and Bruce. We have to continue. We are still left with one more talk. Thank you for your patience and staying with us. So the final talk for this session will be from our colleague Jumiko Oz from Saitama University. And she will be speaking about Japanese collaboration with universities for ground-based optical infrared observations. It's an invited talk. Thank you, Yumiko. Can you please go to the next? Just wait for the presentation to come.
Yes.
With the technical team.
Okay. Thank you. My name is Yumiko Owasa. Thank you very much for organizing this excellent meeting and providing me an opportunity to present our work. This picture was taken at our university observatory. This is Mount Fuji, and we can see both Tokyo Skytree and Tokyo Tower. Today, I talk about optical and near-infrared observations using a variety of small to large telescopes, notably the Subaru telescope and the inter-university collaborative project. Next slide, please. Okay, so my main research is star and planet formation, especially for very low mass objects and their initial mass function. Let me introduce myself briefly. What is a planet, especially outside the solar system? This problem will be also discussed at the IAU Division F meeting on Friday. A theoretical mass-based criterion places the boundary at about 13 Jupiter mass. This is because a brief phase of deuterium fusion occurs at that minimum mass. In addition, isolated objects fainter than young brown dwarfs have been revealed. They do not obtain a central star. This is the first discovered planetary mass object in Chameleon cloud using CTIO telescope. So, and what do you call free-floating planet? Very recently, JWST and Euclid Space Telescope are finding more and more planetary mass objects. Next slide. Slide? Yes, it's there. Yes, yes. Okay. Okay. I'm sorry. Planetary mass objects are analogous to planets, including. Okay.
So for change the slide.
Okay, but not
this one.
Not.
This
Yes,
one,
yes.
and this is
No. I'm sorry. No. Next slide. No. Okay. Okay. I'm sorry. This is a graph for representative mass function. And so it is very uncertain around planetary mass objects. So we are executing near-infrared photometric and spectroscopic observation deep enough to detect young grand dwarfs and planetary mass objects in the various surrounding regions to confirm their frequency and nature and formation. And my main research is IMF, universal or environment dependent. Okay. First, I would like to talk about Japanese largest telescope, Subaru. I have been involved in Subaru project since I was a graduate student. And this is picture is taken at Mauna Kea Observatory. So this is Subaru and this is Subaru. And this cluster is Pleiades cluster, but we Japanese Subaru, we Japanese called as Subaru in over 1,000 years. Subaru telescope's name comes from this beautiful cluster, this Pleiades cluster. So it is located on the summit region of Mauna Kea on Big Island of Hawaii. The summit region of Mauna Kea is one of the best astronomical observation sites in the world. Besides Subaru telescopes, there are 3 other 18-meter class telescopes, Gemini and 2 Keck telescopes. Subaru telescope has been operating since 1999 and has 4 ports equipped with 7 specially developed instruments for optical and near-infrared. Noteworthy, the best angular resolution is 0.2 arcsec without AO correction. This. Our successful observation of S106 were also taken under similar 0.3 arcsec condition. Subaru telescope has a tremendous advantage in observing a wide field of view with high spatial resolution. Subaru telescope is designed for long-term versatility as a major tool in observing astronomy. A variety of instruments have driven a diverse range of science. So, I'm sorry. I'm sorry. Okay, I'm sorry. Especially hyper-superim cam mounted on the prime focus offers an ultra-wide field, about 1.5 square degree. Subaru will add prime focus spectroscopy (PFS) on the prime focus and ultimate Subaru, a wide field high-resolution near-infrared instrument. With these new instruments, Subaru will realize unprecedented large-scale survey observation. PFS is a multi-object spectrograph that covers an ultra-wide field of view 1.3 square degrees and obtains spectra up to about 2,400 objects simultaneously in one exposure. With PFS, Subaru telescope will have 50 times the field of view and 20 times the number of simultaneous spectroscopic objects compared to other conventional instruments. And ultimate Subaru project will implement the next generation adaptive optics system to correct the effect of atmospheric turbulence on stellar image for wide field view. The GLAO system enables us to obtain stellar image of 0.2 arcsecs. It is very, similar to best natural condition of Subaru, but comparable with those obtained with space telescopes. Both PFS and Ultimate Subaru are developed by an international collaborator with many institutions. Collaborations are always welcome. So next, I would like to introduce Japanese small to medium telescopes, including our laboratory telescope. Saitama University is, I'm sorry. Saitama University is here, and Tokyo is here, and NLJ is here. About north, 30 kilometers from Tokyo Station. Our telescope called Sakura was installed by the about 10 years ago. So Sakura telescope has 2 foci and shorter focal length. We have developed the simultaneous imager Musashi, which is dedicated for relative wide field imaging, high throughput and RIZ band simultaneously. So our science main topic is in the following. And of course, our main subject is astronomical observation, but our observatory also provides opportunities and environment for new science education through its activities in order to contribute to developing next generation teachers. Our telescope has 3 instruments. So especially for Musashi, notable point is very high throughput. I'm sorry. So taking this advantage of high throughput, we have equipped Musashi instrument on the other larger telescope at Gunma 1.5 meter telescope. And there are examples of our telescope. Near, I'm sorry, and near asteroid and transit and satellite Starlink. And next, I will talk about 3 Japanese mid-class telescopes, Kanata, Nayuta, Seimei. All of these telescopes are located on the west part of Japan. This Kanata telescope is 1.5 meter telescope, and remarkable point is fast rotating. This telescope have 2 near-infrared and optical instruments. And Nayuta is 2 meter telescope and is research facility and public observatory. NAYUTA is one of the largest telescopes in the world. Means Japan. It was one of the largest telescopes in the world through which visitors can gaze at astronomical observatory. Open to the press. And next, Seimei telescope is 3.8 meter telescope. So notable point is light weighting and fast rotating. Using this telescope, we have built a Japanese telescope network. Oyster project consists of 9 Japanese universities and the NLJ. The Oyster project is designed to promote research using multi-mode continuous observations in the optical near-infrared wavelengths from utilizing the university-owned small to medium-sized telescope network. Our primary scientific object as observational studies in optical near-infrared regime for optical counterpart of gravitational wave and or neutrino source, as well as various other transient and astrophysical objects, such as supernova, flare stars, dwarf nova, X-ray binaries, AGN, GRBs, planets, solar system objects, and PMS. This is a website showing sky monitors in the Oyster. So as a large telescope, Taro 6.5-meter telescope is currently under construction at Atacama site. By incorporating the Subaru telescope into the networks, we can investigate new objects with spectroscopic follow-up observations that are important understanding these objects. There are 3 Oyster's uniqueness points: multifunction, multi-point, flexibility. So we are various mode. Our Oyster project goals are following: exploring multi-messenger astronomical research and education, developing advanced research fields through continuous objects that are difficult with larger telescope alone, and promoting time domain astronomy through focused TOO observation, and improving the research capability of the university through fostering young researchers. So this is one of the Oyster's results. Many telescopes of the Oyster are participating in Japanese collaboration for gravitational wave electromagnetic follow-up, JGEM, conducting optical and infrared follow-up observations. Observations from August to September show that GW170817 is dimming and showing a red color. And these near-infrared data were mainly taken by the IRSF in Sutherland, South Africa. And it is very important to engage in not only extensive science activities, but also productive educational programs, including on-site observations and instrument experience. We have been conducting a variety of educational programs, such as short-time stay training, workshops, and various seminars. This program provides opportunity for young astronomers to stay at an Oyster Institute and use telescopes, instruments, other than institutions to which they belong, and to develop instruments and observational systems. This graph shows the number of PhD, master, bachelor, graduate we have produced in Oyster. One of the graduates in the Oyster project is now working SAO as postdoctoral payloads. This is summary. This. So since you have given me this opportunity, I will go to SAO next week to observe. Thank you very much.
Thank you. Thank you very much, Yumiko. So we have time for questions. Yes, David, go ahead. Then Yoshi.
Thanks for showing all of the various facilities that you have in Japan. I'm just wondering, what's the potential for African astronomers to gain access to those facilities, either directly? I mean, do you have open telescope time applications, or do you have collaborations listed where people could go and look to see where they might collaborate to sort of get access to your wonderful array of facilities?
So you mean Japanese telescope or Subaru?
I mean, for African astronomers to be able to get access to the observing facilities that you have.
Yes. So we are welcome, of course. But now we do not preparing so the collaboration. But now we are discussing international collaboration. So when we will go back to Japan, so we will discuss the possibility for your South African visit.
Yes, go ahead.
Thank you for your nice talk. And I want to tell David that we already have some collaboration with Hiroshima University Telescope, with Kawabata, and also with Professor Yoshida, who I think he's attending our session now. And only I want to ask about you mentioned that Nyota telescope has 357 nights, clear nights. Is that true?
I hear, but Nyota telescope is open and Canada.
But this number of nights are true? This number of nights.
Not. But chief of the observatory of the Nyota Observatory said me, but I don't think so. But you can use Nyota telescope, so please contact me.
Okay.
Yes.
Okay, so I want to point out that we have many collaboration with Japanese colleagues, and Yoshida-san came to Kutami Observatory many times, and they had some repairs for our optical system. We had a problem for many years, and they were cooperating with us to correct for this problem. And I'm thanking him here for his collaboration, and we are willing to continue this collaboration in the future also. Thank you very much.
Thank you very much.
Thank you.
Good. Let us thank you very much.
Thank you very much.
Let us thank once again. Let us thank to all participants as well, because without you, we would not be here. So thank you for coming, and see you in the afternoon after lunch. Thank you. Don't worry. These are the it's the most important is the talk you did it great. I don't have in the northwest. Come, you want to sit?
So that went
you're,
well. I think,
you're waiting for David, or you're waiting? You're waiting for David?
technically, this went a lot more smoothly.
Yes,
than
it was
yesterday.
smoothly because of the communication and the. Marcus, actually, I wanted to speak with you a bit. Oh.
Yes, yeah.
Okay.
If you want to move, then I'll just
Yes,
leave it.
yes.
Yeah, but it's very important not to get closer. It's fine.
Okay, I think it's.
Yeah, just to. No,
Okay.
all right. Yeah, that's good. Yes, 1, 2. Yes, 1, 2. Yes, 1, 2. Yes, 1, 2, 2.
Okay, I think we can begin this next session of our meeting. The first speaker for this is Zainab Awad. If you would like to do your talk, just wait till you get the thumbs up from the tech people before you press the button.
Okay. So, hello everyone. So I'm Zainab Awad from the astronomy department at Cairo University. And first I'd like to thank for the organizers of this session for inviting me. My research interest is in astrochemistry, in particular star formation. And that's why today I want to tell you about the opportunities that we may spread astrochemistry through the African countries. Because if you just go across the corridor, there is the FM2 meeting that is basically for interstellar medium. And unfortunately, none of the African universities are contributing. So today I thought maybe it's good if we just talk about astrochemistry. So during this talk, I'm going to tell you what is astrochemistry for those who don't know, why we need it, and then what are the possibilities to have astrochemistry in Africa, challenges, and some future perspectives. For all of us, we know that astronomy is concerned with motion positioning if we are doing astrodynamics, or it's for the formation, evolution, development if we are doing astrophysics, either observationally or theoretically, and I'm doing theoretical astrophysics. And astrophysics has several subtopics, and one of which is molecular astrophysics, in which we are looking at the universe through the molecular emissions, and we are looking for the looking into the formation and destruction of species. And species, they don't need to be molecules, but also atoms and ions. So any nature of the species we have. Hence, we blend astronomy with chemistry, and that's why commonly molecular astrophysics is called astrochemistry. So far, we have more than 200 known and confirmed species in different astronomical regions. And these species range from simple molecules, like diatomic molecules, like CO, up to the largest molecules. And we start in astrochemistry to say large molecules if we have 6 atoms together. So the first larger molecule we have is methanol, which has 3 atoms of hydrogen, 1 carbon, and CH3OH, actually 4 hydrogens. So, so astrochemistry is very important because when we studied astrochemistry, we now know that we can either, with astrochemistry, we can either characterize the interstellar medium. And in that, we may look in the main components of the interstellar medium. And interstellar medium is the space, the material that fills the space between stars. And it's made of gas and dust, and we look into the different components of the gas and the molecules that are formed on the grains, and that's why we may look at the main components. Or we also can have the physical parameters from the density and the temperature of different regions we are looking at. Also, we may characterize the interaction with radiation to get an information about the extinction, for example, of the radiation in a specific region. This is the first thing we can do with astrochemistry. The other thing that we are interested in is the chemical processes that goes into the interstellar medium. And these processes takes place either in the gas phase, so all the reactions happens in the gas, or they are taking place on grain surfaces. And of course, there is a mutual interaction between both, because in order to have reactions on the grains, species has to land first from the gas. They go and do some surface reactions, and then by one sort of desorption mechanism, they return back to the gas phase to enrich the material with more complex molecules that we cannot form by any means in the gas, and one of which is H2, which is the most abundant molecule in the interstellar medium. That's why chemical processes, to understand chemical processes and how they form and destruct molecules, it gives you insight on the chemical reactions and the evolution of the material. So by studying astrochemistry, we now know that it's not working. Do we have a technical problem? Yeah, so, okay, thank you. So by studying astrochemistry, we now know that we live in a molecular universe, and for different regions, we have different characteristic molecules, as well as different physical parameters. So we can just divide the interstellar medium or the regions there according to different parameters like temperature, density, cosmic ray ionization rate, and the amount of radiation field these regions are facing. These quantities can be translated into other quantities that our observers can understand, like the wavelength frequency and the photon energy that can be translated by knowing the temperature of the medium that we would like to observe. And hence there is a connection between theoretical work and observations, because we can, with our models, we can predict what molecules that we would like to observe. And then we ask our colleagues who observe to look at these molecules for us. But of course, looking at molecules is different from looking at atoms, because for atoms, we have only electronic transitions that need higher energies. But for molecules, we have different transitions, like rotational and vibrational transitions that have different energy levels. And hence, we are looking at them in different electromagnetic radiation. But one has to be very careful when you decide which band you want to observe, because of the atmosphere that blocks a lot of radiation. And then if you can see in this diagram, so we can have the optical and the radio bands arriving at the Earth, some of the infrared, but other infrared, they need to be observed from space. Okay, so why do we need, what's the opportunities to have astrochemistry, and why we can have astrochemistry in Africa? Of course, we have a lot of observing facilities in Africa. In optical and near infrared, we have observatories in Morocco, in Egypt, and in South Africa, where they have also some infrared observations. But unfortunately, optical and near infrared, they are not useful for astrochemists. Astrochemists, they do use observations from the infrared bands, but we look at the grain components using the mid-infrared and the far infrared that are not, as you can see, that are not accessible from ground. So we have to have space telescopes, and we don't have this facility at all. So of course we can have the data, but I mean, for ground-based, they are blocked. So now let's see what radio can provide us. And the next era is for radio astronomy. As you can see, all the expression beneath this floor, they all about radio. So radio data provides us with wealth of information. And now in Africa, we have in South Africa, we have different telescopes, one of which is Mercat. Of course, not this little cute creature, but the one that is the first phase of the SCAMET, which is the second phase of the SCA law that is located in Australia. So I believe that astrochemistry as a field of astronomy is really promising to go in, to have progress in Africa and between African countries. Let me tell you what, as astrochemists, what we benefit from radio. One example is the process of massive star formations that can be traced using a lot of molecules that have transitions in radio in different wavelengths. And of course, these are the high frequency radius. And each of these stages of the formation of the massive molecules can be detected with special maser lines in the gigahertz band. And the most famous ones are water and methanol masers. They are tracers for the massive star formation process or stages. Not only we benefit from the high frequencies, but also low frequencies. They will give us a unique insight on the chemistry that goes into the interstellar medium. That's because we can know something about the first molecules that has been formed by looking at the chemistry of the early universe, because we are looking at very low frequencies that comes from the early universe. Also, it tells us something about the first objects that formed, in particular during the cosmic dawn and the reionization, when the first stars formed, and then their UV radiation started to reheat the medium, and then the gas is reionized again, and I'm almost done. And that's how the low frequencies are very important. So we have wealth of information that we can get from ground observations, as well as space facilities. And all of this tells us that astronomy is not just about science and research, but it's also engaged in technology, in improving our skills, knowing something about the origin of the universe, and that can inspire more about it. And hence, in order to be efficient working in this kind of network, we need to build a new generation, and capacity building is going to be the first step in order to form our bonds together as astrochemists, and to spread astrochemistry in Africa. But of course, we have a lot of challenges for this. Not only the well-known scientific challenges as astrochemists may have, but we also have other challenges while building these bonds. First are African. When we are building the African bonds, the most challenging thing is that we are working as isolated islands. So none of us knows what the other is doing. So this is one very critical point. And also in different countries, we have poor facilities, and good researchers, they usually go outside and they never return back. So we lose a lot of manpower in this. With African International, we don't have enough educational programs in astronomy, either for undergrad or postgrad. Sometimes our programs are not qualified from the international institutes. Also, our portfolio is not as high as the other researchers from the European or the America. So we have a low rate of publication due to lack of funding and other things. Also, because of lack of funding, so we are shortage in some skills. Of course, for building both, we have other common challenges, like the funds, the mobility, which is one of the biggest issues, and sometimes the language barrier is also a challenge. To overcome these challenges, I thought we have to strengthen our collaboration African collaboration and African international collaboration that will allow us to access the data, and hence we can just exchange these data and start to build our knowledge about how to do the data analysis and so on. Also, the capacity building, we have to invest in STEM education. We have also to develop the infrastructure, having more labs for data analysis with better infrastructure like computers, internet, and so on. Also, we need, and this is the most important part that we need, is really to have policies that attract the talents and return them to their countries. Also to encourage the astronomy research and to ease the mobility and remove restrictions. And maybe we all face some of this as African nations. We have to also raise the awareness of the astronomy, including astrochemistry, and that can be done by telling people that astrochemistry may tell us about the origin of life in terms of molecules, not in terms of any other thing. As science diplomacy is one other thing to think about, in which we all have the right to conduct science. And that's it. Thank you very much.
Thanks very much. I just want to, before I open questions, just say how what you just said in those last slides aligns so much with what the African Astronomical Society aspires to do, to get rid of silos, to promote collaboration within Africa. So thanks very much for that.
Yeah,
I'm opening the floor for questions. You can have a mic, thanks.
Hi, Zainab, a wonderful talk. Thank you so much for promoting and bringing together astrochemistry here on this continent. And I fully agree with the chair that those last slides were very much aligned, I think, with what the African AFAS is trying to do, and that you will help, that you will have help from AFAS. I was wondering a little bit more. I know that this particular session is on facilities in Africa, but more and more research is actually being done with archives from some of the big telescopes. And of course, for astrochemistry, we have a wonderful machine. It's located in Chile. It's not located in Africa, but ALMA has a fantastic archive, of course, with where one can define lots of astrochemistry projects. To what extent is sort of your community here in Africa thinking about that, or do you lack sort of resources to be able to use ALMA data?
Let me talk about Egypt, because most of my experience is in Egypt. I don't know about the other African countries because we work as isolated islands. So in Egypt, we don't have a radio astronomy research group. And but we have a couple of people who are doing radio data analysis with the help of people from Maryland, for example. And I know that you can just count them on one hand. And that's why I started to have an interest. Maybe we spoke about it yesterday. I started to have an interest in radio astronomy, and I spoke with my colleagues at the astronomy department at Cairo University, and we decided to have a very small group of astronomers who are interested in doing radio astronomy. But the problem is we don't have an expert to give us the training. And what we are trying to do during this session is to find collaboration with radio astronomers who are willing to teach us about the data analysis, because for the time being, we are only 3 persons. And we have downloaded software and everything, but it's really
It's
time
hard.
consuming.
It's hard to use.
It's time consuming without an expert. So we are doing our best to find bridges and to build bridges with.
I think
radio
this is one of the
astronomers.
reasons that you started the hands-on workshops, especially to train in one
Yes.
particular facility, whether it's X-rays or radio or millimeter
Yes.
to
And
train,
this
or
kind-
JWST,
Yeah.
to train people in a region in the use of those data sets, because they're fantastic data sets. But
Yes.
I agree with you. It's you need a bridge to be able to use them.
Yes, that's true.
Yeah,
that's true.
Good. Thank you.
Okay, we got time for one quick question. Yeah.
I am from Nirang National Research Institute of Astronomy, also in Cairo. We have a lot of experience in radio astronomy. We have a lot of experience of people work in spectroscopy. But I think there is no calibration inside Egypt itself. That's the main problem. We have a lot of experience in Riyadh.
In radio data analysis?
Yeah.
Okay,
Also,
this is something I know only one person from Narieg who is
more
doing.
people. And also people work in spectroscopy, in optical spectroscopy. A lot of people, we have good experience with data reduction, etc. But the main problem, there is no calibration inside Egypt itself.
Yes, as I said, we work
before
as.
we look for collaboration with another country, we must first apply that on ourselves.
Yeah, but we don't have radio experts. Again.
No, we have. I told
No,
you we have.
you
I think you can take
your...
this conversation over a nice Egyptian coffee.
Yeah.
So
Thank you.
Let's thank Zainab again for the talk. It's a pleasure for me to welcome my friend Yosri to give the next talk, which is on this exciting new project, the Egyptian Large Optical Telescope.
Which one can you use?
This is the next. This is previous, and this is a relay. And if you ask people on this mic, it's too sensitive. We can just give it a cap.
Okay.
Yes.
Okay.
No.
Okay, thank you very much. And my name is Yusri Azzam. I am mainly an electrical engineer working at the National Research Institute of Astronomy and Geophysics in Egypt. And I am the technical lead of our staff in Nariag, and the technical lead also in this big project. And I'm going to give you an update of our future Egyptian Large Optical Telescope, which it is envisioned to be 6.5 meters telescope. So I want first to tell you that astronomy in Egypt started early in maybe in 1937 or 39 in Polak Observatory, then moved to Abbasiya Observatory in 1839, and then moved to Abbasiya Observatory in 1872, and then we moved to Helwan Observatory in 1907 by Reynolds telescope. This telescope. And then after that, we have the Kutumaya Observatory, who started working in 1964. This Kutumaya Observatory is still working now, and it has very good instruments, what's called KFIS, Kutumaya Faint Image Spectropolarimeter. This telescope, this instrument, which has the 3 modes of operation to observe in photometry, spectroscopy, and polarimetry. It is a good instrument. It's very advanced instrument that worked in this telescope about 4 years ago. And we have
working groups that are observing transients and near Earth objects, and it is going very well. And many published research has come from this instrument actually. So why we are looking for another telescope? We are looking for another telescope because our Ptolemy Observatory is becoming more and more light polluted because of the construction of the new capital, the new administrative capital. The government started working on this administrative capital in 2016. And so we can see now the building around our telescope like this one. And this is one of the photos of the night sky at Ptolemy Observatory. So I think that Ptolemy Observatory will not be able to work in the coming 5 or 6 years. And we have to look for another place to build a bigger telescope. So also, as we can see here, there is a lack of telescopes in this part in Africa. And we showed today and yesterday, many people are saying that there is no telescopes in this area of Africa continent. So we need to have another larger telescope in order to fill the gap between Asia and America, and also between Europe and South Africa, and to be also as a regional telescope for the MENA region, to be able to have some continuous observation instead of the Ptolemy observatories that is envisioned to be closed maybe within I don't think that it will work for more than 8 or 9 years. So we started looking for good candidates to search for good place to construct or to build our new telescope in, and we found these parts of mountains in Egypt, in Sinai Peninsula, and in Red Sea, just west of Red Sea, and this also the area. But this area is not good as it has many sandstorms, and they cannot be good for this astronomical telescope. So we looked for this area in Sinai Peninsula and this area in west of Red Sea. And yesterday we showed our colleague Muhammad Darwish presented his talk about searching for the good place, the best places in these two areas. And his findings, as you can see now, we found he searched seven of the mountains in the Sinai, in the Red Sea area, and also he searched for another 3 mountains in Sinai Peninsula. And his findings, and after that, before that, we have a lot of field trips to these candidate sites from our colleagues that continued for maybe 5 years before, during, and after the pandemic. And people try to visit these mountains to be able to find the best places or the roads to get into these mountains. You can see now these field trips that continued for 5 years. So the candidate site research study that Muhammad showed yesterday searched for about 7 parameters to atmospheric criteria affecting the site location. He used the ERA 5 reanalysis that covers more than 40 years of graded data with spatial resolution and was about 30 kilometers, and he had this research published in monthly notice, this one, and he used these parameters for criteria, as criteria for looking for the best location or best sites to build this new telescopes. He actually he was able to get these 7 locations or 7 sites. And he found that the best sites are the mountain or the site 3 and site 4, which are in the Sinai Peninsula, and the other one in the Red Sea. This one is called Rujum Mountain, and this other one is called Zubair Mountain. And we can see now the Zubair mountain supersedes the other mountains, the Zubair mountain in the overall score. Also, this finding has been reached also through collaboration with our colleagues in Spain. They made similar research, but they didn't publish it yet. And they have similar findings from their study. And so we started looking at these two sites, at Rujum and Zubair. The Rujum is in this Rujum is in Sinai Peninsula, in this location, and the Rujum at this site of Red Sea. But actually, due to the accessibility problem in the accessibility problem in the Red Sea location, it was very difficult to get road to that location, and then we started working in only in Sinai Peninsula location in Rujum. We started by getting 2 copies of dim stations, tower, dome, and all sky camera, and we already ordered them, and we got them actually from Astelico from Germany. So these instruments have these parameters, the optical parameters of the dim station is as you can see here, and also the all sky camera has similar has very good parameters actually, and it has records for weather parameters, relative humidity, and external temperature, and it has also a separate module for attached to the camera which measures wind speed, wind direction, and atmospheric pressure. So we started working by finding a good road to Sinai Peninsula site. As you can see now, the road was very bad, and we tried to repair it in order to be able to get into the mountain with our cars. We started making the foundation stone in order to have some information or to give the media that we are going to build a new telescope in order to have some funds from the government. Our ex-president of the institute bought this foundation stone in Sinai Peninsula. We sent or transferred our instruments to that place, as you can see now, and we installed the internet satellite communication in order to be able to communicate with other people, with other world, because we don't have any network communication at that place, because we are 120 kilometers inside the mountain. The nearest city is 120 kilometers, so we can not have mobile communication in that place. So started working in installing the instruments with Astelico people. As you can see I'm working here with them. And here also, you can see me here now. Because summer is very hot at that place, and we're trying to finish as soon as possible in order to finish and to go home for these problems. So I want to show to you some of the sample images at that place. We can see now the Milky Way is very nice. This is very nice. This is actual photo from the Sinai Peninsula site, and this is all sky camera images also. And this is another all sky camera image, and this one was fixing the camera and for about 2 hours and see the around the North Pole that you can see. And you can see very good images for Milky Way and at this site. And the initial seeing value at that site was 0.7, which is very optimistic and very maybe will be very good. So the future work will continue hardware and software installation. At the start site testing campaign, we will install solar power cells for total remote and robotic operation, and try to repair the road to Red Sea site in order to start site testing in the other location, in order to be able to compare results from instruments from both sides. Also, we'll prepare other necessary instruments for site testing, like dust sensor, sonic anemometer, scintillation detector, and ranging, and other instruments that can measure the turbulence. But we have really some difficulties and some challenges. The first challenge is the urban extension and touristic development, especially near the touristic place in Red Sea area, which is threatened by touristic developments and urban extension. Also, we have site accessibility and security issues related to this location. Also, same location at Red Sea. And also, science and engineering personnel are very few, and for such a big project, and we have to make new jobs for this personnel in order to be able to start working in this big project. Also, we have to define scientific priorities and science case for our future Egyptian Large Optical Telescope. And we have to foster our experience related to site testing in order to be able to analyze the data coming from site testing campaign. So I started about 2 years ago to looking for this fostering of information related to site testing and dark skies, and I suggested this focus meeting actually with my colleagues, with David and those other colleagues from Morocco and from all countries, in order to be able to get some information about the future telescopes in all Africa, and to try to treat the problem of dark skies and to keep dark skies in all countries, because we are suffering from this problem many years ago when we are in Hilwan and then moved to Kuttamaya, and then we are now moving to another location because of we were not unable to keep the dark skies at that locations. And I started working with our colleagues in order to define the key points of this focus meeting, in order to pay attention of the Astronomical Union and to African countries or African Astronomical Society about our future telescopes and how to keep them far from the light pollution and so we still need actually to setting up international scientific advisory committee to give advice about science goals, recommend on defining the instruments suitable to reach these goals, and facilitate getting training and inspecting visits to similar telescopes around the world. Also, we need to ask more jobs in science and engineering personnel, and we have to make legalization to protect dark sky at the chosen sites for the urban and the light pollution, and to have fundraising from multiple channels is necessary with a return of investment plan. And also we are open to collaboration with other countries if we some countries, other countries. Yeah, I'm about to finish. So I think this is the final one. We are very open to and welcoming any regional, African, and international collaboration agreements to provide any sort of support to this big project in order to be existing observatory. Thank you very much. And,
thanks very much, Yosri. I'll take the benefit of being the chair to ask the first question, which is, how far advanced are you in developing a conceptual design for the telescope?
Actually, we don't have yet detailed information about this design, but we have the information that it will be 6.5 meters telescope, but we don't have actual information about this, and that was one of my ideas to seek for this information in order to be able to get ready for the design process.
Thanks. Other questions? Yeah. Other questions? Richard?
Yeah, Sinai Desert has long been known to be a fantastic site meteorologically, but you mentioned security as a challenge. it's not so far from one of the most socially volatile places in the world right now. Is that a risk factor that concerns you or not?
No, because our Sinai Peninsula is now a safe place, but maybe previously it was not safe, but now we can cross anywhere and we can go anywhere at that place with no problems. We have support from the government officials. That government says to us, okay, you have to go and you have to do all work, and if it is nice, it will protect us. No problems actually there.
One last question from Eddie.
You mentioned seeing value. You mentioned initial seeing value of 0.7 arc seconds. Over what length of time was this measured and with what instrument?
By the DIM instrument.
Over what
It is
length of
only
time?
one night. Into one night, we got this in one night because we have problem with the servers that controlling these instruments. The server was broken, and we were trying to repair it, and we got very many computer to try to make these instruments working, and then we get this result from this mini computer that was not so perfect. We are waiting for this server to be repaired in Germany, and after coming back to Egypt, we will continue our work to install this server and start the campaign of site testing.
Okay, thanks very much, Yosri.
Okay, thank you.
So the next talk is by Itzia on the impact of ground-based telescopes and the formation of next generation astronomers.
Oh. Okay, you tell me if you need me to change. Okay, thank you so much. Maybe you are as surprised as I was to be invited to this session, because what is a Latin American astronomer doing in a session devoted to the development of the African community? But just upon reflection, I realized that I have had the honor, and I have the honor to be working with the young community in Africa, in different countries in Africa, through this important program led by the International Astronomical Union, which is the International Schools for Young Astronomers, supported by the Office for Young Astronomers. So I'm going to base my talk today on that experience. There you go. So for those that do not know the program, the International Schools for Young Astronomers have been organized by the IAUs in 1967. I joined the program in 2016, where I was in Iran in one of my first schools in the role of deputy director. And we have, I will take the time to just make the announcement that we have the Office for Young Astronomers meeting tomorrow for those interested in the program. So throughout the years, and we rotate these schools in different continents, we have had more than 1,500 students, but I have had the pleasure to work with at least 100 African students in the 3 schools that are posted here. 2017 in Ethiopia, 2018 in Egypt, 2023 in South Africa. The program runs for 3 weeks, is intensive. The selected students that come to the school are in general graduate students doing masters or initial PhD studies. They tend to be isolated in the sense that they might have a lot of experience in one topic where their supervisor is working, but little exposure to a broad content
of astrophysics. So in these schools, we provide with classes, we provide with labs, we have observational classes, data analysis, they work on small projects, and through 3-week intensive work, they become a little community that they know intensely each other and their lecturers. And what we have found is that through time, that network gets carried through in their lives, in their professional lives. So the goal is to broaden the participants' perspective in astronomy, and they are actually aided by a team of faculty, which are typically 10 to 15 people who are world-class researchers that work through these 3 weeks with them. Okay, so from the very beginning, the schools were focused on optical astronomy. So the program has a lot of experience on what is the impact on the young for optical astronomy. Now, I have to say that since I joined the program, and because I'm much more multi-wavelength, I have been trying to say, yeah, optical astronomy is important, but there are other wavelengths which are important. And so we also focus now on radio, millimeter, X-ray, gamma ray. We never have had gravitational waves, but I'm hoping that one day we do. And certainly also we promote the use of computational astrophysics, all tools that can be used in order to create the next generation of scientists in this continent and the other continents that need our help. So this is just a set of photographs so that you see what happened in 2023 in the school in South Africa. We were here in Cape Town and we went to Sutherland to do optical practice. And you see here the group of 30 students that came to visit SALT. They couldn't do practice with SALT because obviously it's an oversubscribed telescope and very much appreciated in its time, but they actually had the privilege of being seeing how the observations were conducted. They actually had the training to see how they could apply to SALT time, and they could use the smaller telescopes, the 1 to 2 meter class telescopes, to acquire data during bright time, which then they didn't use for their practice because they were given beautiful SALT data to do the practice with. But at least they actually acquire their own data once in their lifetime. And you can see here one of the sessions of actually acquiring the data. And the gentleman here is Antoine Mahoro. I mean, he was one of our alumni in 2017 in Ethiopia, now graduated here in South Africa, I believe in the University of Cape Town. I might be wrong about that, but in one of the South African universities, and now an assistant observer for the SAAO telescope. So he was actually training the new generation of students that came through the program. And this is one of the classrooms in which they were also doing data analysis. Okay, so through the years, we have used different facilities. This is just a list of the facilities that we have been using in Ethiopia. We were supposed to use the twin 1 meter telescopes. The photograph is here. I'm saying we were supposed to because we were weather out of taking data, but the students could do practice with optical data having been acquired before. A lot of the work for all this training is done by the local lecturers. So in the case of Ethiopia, Mirjana Povic did all the spectroscopy training, and Leonid Berdikov, all the photometry training. In Egypt, again, we were supposed to use the 1.9 Kotamia Observatory, weather out. We are not always weather out, but in these two occasions we were. Somaya Saad was coordinating the team of lecturers that were working with the students. In Colombia, 2018, not Africa, but I think it is worth commenting the case of Colombia. Colombia doesn't have an optical telescope to do practice with. I mean, they do have historical telescopes. But we actually invited Karim Menendez del Mestre, an optical astronomer working in Brazil, and she got time in the a 1.6 meter observatory Pico dos Dias in Minas Gerais. And this is a photograph of her class doing remote observations with a telescope in Brazil from the mountains in Colombia, where they will never build a telescope there because it's cloudy a lot of the time. China, we use the 70 centimeters Sinotai telescope, the 1 meter telescope in Kunming. Then we had a hiatus of time due to the pandemic where we didn't have any schools. I already mentioned South Africa, 1 2 meter class telescopes in Sutherland. And in Mexico, we use an in-campus 1 meter telescope that students could also touch and use. So I'm going to mention some of the projects that students typically are trained with. All these projects are research projects the lecturers brought to the school for the students to do practice. I mean, most typically students did not work on those topics before. Some of them actually took the data, analyzed the data, were enthused with the program, and were recruited by the lecturers for their PhD programs or to work remotely with them, or they took the data and analyzed it for bachelor's degree or master's degree in their own universities back home. So our students are not just local to the country that hosts the school, they are regional. They come from countries surrounding the host country that I have mentioned before. Okay, so let's just go through some of the programs. I mean, this might not be a surprise to you of using optical telescopes, but for training students, it's actually very useful to work or to focus on variability programs, because those are programs that have been established through time, and the students can contribute with 1 or 2 nights observing, and suddenly they feel part of the team, that they're contributing with something that they see the big picture of. I mean, they can see maybe years of data having taken on an object, and suddenly they are contributing with a few points, but it is their first experience in this type of telescopes. So this is the program that, oops, I went forward without wanting to do that. So this is the program that Erika Benitez brought to the program in 2023 in Mexico. We use an in-campus. I mean, the in-campus telescope means that we are living by the telescope, and the classrooms are there and the telescope is there, and you can touch the telescope every single day if you need to. So the monitoring program for AGN that she brought to this school is a program that she has running in this telescope. It's very near Puebla City, so it's very heavily polluted. But still photometry can be done. And these are just the type of light curves in urban that you can see this Markarian 421 object doing. And so this is the program of observation. She is Erika. Just put the students through 3 nights of observations at the telescope in different groups. They were acquiring Johnson photometry, analyzing the images, isolating the quasar emission, and just putting it into the light curve so that they could see how it had varied in the days that they had acquired the data. And these are just 2 of the Latin American students participating in this workshop for data analysis, one from Mexico and one from Ecuador. The Ecuadorian student actually is studying black holes, doing theoretical work. This was his first ever experience with observational data, probably his last experience with observational data, unless he really was convinced that this is the type of thing he wants to devote to. But it's so important that even if you are doing theoretical work, you have some observational experience, so you can analyze what you can believe out of the data. I mean, of course, data is gold. I mean, it's our gold standard. Our models have to adjust to data, but data have caveats, and you have to have taken data in order to understand those caveats. And this is one of the lessons that one can take for this type of programs. In China, I mean, beautiful observatory, lots of remote observing. We could only use the remote observing in order to just get the data for their students to work on. But they had this beautiful program of having different objects, variable binaries, binary stars, pulsating stars, contact stars, likewise crowded fields. I mean, very difficult. I'm an extragalactic astronomer, so whenever I see something like that, it's like nightmare. I mean, how do you isolate the photometry of a single star in that crowded field? But that's the type of problem they were given in order to contribute to the light curves that they were taking with these facilities. And again, this is Mbanquian, the leader of the school, and the lecturers that contributed to this program with their own research program for the school. In Mexico, again, this is a program that I think is very cool, is variability of asteroids. And this is part of the International Asteroid Warning Network. And this is work that it is being done with a historical telescope, a 77 centimeters Schmidt camera from the 40s. I mean, this is where the Herbig arrow objects were discovered, okay, still in use. I mean, we don't get rid of infrastructure in Mexico. We don't have that luxury. Any infrastructure that still works is going to be used. This is being used for research on asteroids these days. And this is our 2-meter class telescope in the north of the country. And so with these two telescopes, the students in Mexico also acquired data. And they did both photometry and spectroscopy. And this photometry and spectroscopy could be used in order to contribute to the monitoring campaign, which is an international campaign. With the whole collection of international data, actually, the researchers can study the morphology of the asteroids doing light curve inversion. And they can study, of course, the orbits of these near Earth objects. So this is very important in order to prevent, well, you will never prevent, but at least you will know you are going to be hit by a big thing on Earth, right? So again, very cool program, I think, that shows how small telescopes can be used for research and actually can have an impact on the young people in our communities. Okay, so apart from those, we have had other programs. In Ethiopia, I mentioned we were weather out, but usually we have CAN data taken previously in that telescope or in other telescopes the students can work with. And in that case, it was programs on active galactic nuclei and stars. In Egypt, there was a whole program on clusters of stars also prepared for the students. Colombia, I already mentioned, but Colombia also had a quasar variability type of project. China binary stars, Mexico blazar variability and asteroid classification. And in South Africa, the students had the luxury of being served spectroscopy of salt on AGN, supernovae, all sorts of galaxy types to get analyzed. So let me just describe a little bit now the impacts that these programs have on the students. So this is feedback from the students themselves, students that never had seen a telescope before and that suddenly are brought to an infrastructure if they are physically there, or they're shown what they are going to be using on a screen. And this is the general reaction, is loving absolutely that they are taking their own data. So this, I'm a big fan of Twitter, now X. This is one of the Colombian students we had and said, and she says, we're going to observe 5 quasars tonight. Yeah, right? I mean, she's so enthused. And these are just some of the comments. Thank you for the training. This is the first optical observation and I feel so much pleasure. I really like the observing nights. And as someone who has not yet worked on such activities, it was a great experience. I wish there were more. That's the general comment for all students. I mean, they really would have liked to acquire more data, have many more nights. 3 days was too short. And we normally ask the students, I mean, these are just general comments that they can send, but this is just our feedback form that we ask them to fill in. So whether they felt the project was challenging, normally, so if you see deep blue bar, it means yes, absolutely yes. If you see something which is red in the ones, it means that they completely disagree with the statement, right? So you can see blue bars everywhere, which basically mean that they are very satisfied with the training that they have received, right? So project challenging, time spent on the project was right. Well, there is a distribution there. The lectures prepare me for the project, again, distribution. The tutoring I got for the project, they always have somebody watching over their shoulder so that they are not screwing up with the data reduction is fine. The supervisors were great. The observing eyes were good training. I would have liked to do more observing. And then, well, of course, for SALT, of course, everybody was interested in SALT, right? So this is my last view graph. Again, this is just a photograph of the students there. And I think upon reflection, there are a few things that are worth taking into account when we think about the value of optical telescopes. And I will focus on small optical telescopes because I think everybody agrees that the 6 meter in Sinai or SALT is a great facility. Of course, we see the papers coming out of that, but 1 meter class telescopes have much less focus, and there is so much to learn from them. So high engagement is the first thing I will say. People love that they are taking their own data and that they are analyzing their own data. They learn observational planning. Now, this is something that you will miss if you do all your research with databases, which is great. And it's something we encourage as well, of course. I mean, there is so much beautiful data from ALMA, from JWST that we can tap into in order to do research. But data planning is something you will always miss unless you take your data at least once in your lifetime. You learn to prepare thoroughly through the night. With my own students, I used to do millimeter wavelength single disc astronomy. And I put them through the drill of counting how many minutes of telescope time they have wasted idly. And I charge them symbolically $10 for each minute that they have wasted. Very soon, they don't waste 1 minute idly on a telescope. I tell you that. You learn how to deal with frustration because we all have gone to a telescope and been clouded out. And then you have to actually learn what to do with your time. Or sometimes you can actually adjust to the conditions and just shift from your A plan to your B plan. So B plans are important, and it's a good training for the students to have when they go to small telescopes. And they learn observational caveats and uncertainties that otherwise they will think data is perfect. But when you acquire the data, you know that that's true. They learn how to analyze data. They design their own observing proposals. And they learn how to be systematic on recording data intake conditions. None of this can be done with archival data. This is done only when you have your hands on the telescope. And doing it at least once in your lifetime is something important, is a lesson that you carry through your life, I will say. Thank you for your attention.
Thanks for that inspirational talk. So questions? Patricia.
Thanks. That was wonderful. Obviously, very impressive. I'm wondering if you mentioned your interest in multi-wavelength data. Do you also teach them virtual observatory tools so that they can match the observations they've taken maybe with X-ray observations or radio data?
Yes. So since I joined the program, but I had my first splash with making an impact on how we teach in the program in 2017 in Ethiopia. So of course, the Ethiopian observatory was being built. Actually, I think we touched the telescopes for the first time in the school. But I had an emphasis. Okay, Africa cannot do without radio astronomy, especially because of all the effort with MeerKAT, SKA, and also the African VLBI network. And so we invited a radio astronomer to teach about radio astronomy. And for each school, apart from optical astronomy, which I think is very intuitive, and so it is good to have optical astronomy in the mix, there is always one other wavelength. So it can be X-rays, it can be radio, it can be gamma rays.
But
sometimes radio.
specifically virtual observatory tools.
As well,
so-
yeah.
Okay.
Sorry.
No.
So apart from that, we also always have a virtual observatory class. Definitely, very important.
Okay, I think we better move on. Let's thank Itzia again. So the next talk is by Cyril on observations done in Kenya.
Thank you. While the slides are being put up, I'll just say thank you very much for the occasion to present about this project that we've been working on for a couple of years now. This is the result of a work by a team of people. Most of them are mentioned there, but probably not everyone yet. So thank you very much to all the team. So I'm going to tell you a little bit about work we've been doing, installing a 40 centimeter in Kenya, originally to observe the impact of the DART mission into an asteroid. And so I'm going to start a bit by telling the people here that I might not be familiar with DART, what this was all about. So Itzia actually gave a really good introduction to that, talking about asteroids and what happens in asteroid is en route to the Earth. What do we do? Well, that's why we've got planetary defense. And that was kind of the first test of, well, can we nudge an asteroid to the side if it's coming towards the Earth? So it's testing what we call the kinetic impactor technique. So the spacecraft crashed into the asteroid on September 26, 2022, to see how it would kind of change its trajectory of this binary asteroid. So it's crashed into the smaller of a pair of two asteroids. And one of the main objectives is see, well, how much is it going to nudge it away, basically. And a way to measure that was to observe it from the ground, because, well, when you crash a spacecraft after the asteroid, after the crash, you don't have any spacecraft left to observe what's happened. There was a bit of a CubeSat, but I don't have time to go into all those details. So there was a huge ground-based campaign to observe what happened there. And one way to do that is basically because the smaller asteroid was eclipsing the bigger one. If you look at the light curve, you could see the period, how long it took to have a turnaround and whether that changed after it or not. And so there was a huge, very international campaign that was set in place to actually say, well, how successful was this mission, or how good is this technique as planetary defense mechanism? And the slide here shows all the observatories on Earth that were part of this observing campaign, several observatories in space as well. But you might notice this red circle there. And so that's where the asteroid could be visible from at the time of impact below Air Mass 2. And you can see it was mostly, well, the southern western part of Africa and not much else, not where most of the bigger observatories are. Well, obviously South Africa has a lot of telescopes ready to observe, but well, what if South Africa is cloudy that day? That's going to happen once, right? You don't want to rely on one or two telescopes, one in Namibia, region there. So you don't want to count on a handful of telescopes that could be weathered out. And so we kind of discussed with colleagues and noticed that there was a bit of a hole over there. And that's how this whole project came about, because that telescope there in Kenya didn't exist before 2 years ago. So we started from the University of Edinburgh, the leadership of Colin Snodgrass over there, discussing with people from the COTI initiative that Eddie mentioned yesterday. They'd been building the case for an observatory in Kenya since 2017. 2017 had some funding for meetings, for site tests, to run weather model, to identify sites. And it's a partnership between the UK ATC in the UK, University of Ireland and SAO. I encourage you to go check the website if you want more information. So COTI had been in touch with different partners in Kenya already, the Technical University of Kenya, that provided local contacts, local expertise. And the final piece of the puzzle was the Turkana Basin Institute, who had different research institute in Kenya, mostly tailored to anthropology research, but they had local infrastructure in very dark and dry region of Kenya. And so we're able to support kind of our endeavor to install a telescope. So with this team, we started putting in place, the logistics of it, shipping a telescope to Kenya and installing it in Illoret over here, the very northern part of Kenya on the side of Lake Turkana. Why Illoret? So previous studies had shown by Eddie Graham had shown that there are potential very good astronomical sites in Kenya. Some of them are very remote. And so the good thing with Illoret, there was a camp from the Turkana Basin Institute. And so we had buildings, you know, places to stay, water, electricity, all that kind of small things that make things a little bit easier. So that's where we installed a telescope. They're extremely helpful in helping us with all the logistics of bringing and installing a telescope there. And with 2 weeks to spare before the impact, we're ready with a 40-centimeter Dobsonian telescope with a small CMOS camera installed at the Turkana Basin Institute. So I said it's not a world-class astronomical site, but it's still in the very dark region, fairly clear, and we were able to install the telescope. So at the time of the data impact, we were ready. We had a team from observer from the University of Liège and the Technical University of Kenya, and representative from the Kenyan space agencies as well came for the launch. And this is what we observe. Yes, it works. So you see, you saw the little dot in the middle, that's the asteroid. Actually, it's the bigger one we see. And at some point you see kind of this plume going away, so that the spacecraft had hit the asteroid and there was a plume of, we think, probably sodium just blowing away. And that's just over the span of probably 10-15 minutes happening. So that's real image taken with this small telescope in Kenya. We started observing about 2 weeks before the impact, up to 2 months after. So there were people for about 3 months on site all the time, observing as much as possible. And what's really kind of special about our setup compared to others other sites were luckily clear as well to observe the observation. But we had this CMOS very fast camera, and we were really obtaining very, very high cadence observation. So we could really catch this very fast plume that left the system within only a few minutes. And that's kind of the light curve we got from the asteroid, different apertures there. But the really interesting thing is that this very fast rise, we're one of the only ones, if not the only ones, to get it with that, at least that cadence, this very few moments after the impact. So actually this small observatory in Kenya really made a contribution to the support of the DART mission. And Andy over there, I'll let you confirm that later. But yeah, we actually made a contribution with this small telescope. And luckily that's not the end of the story of this telescope in Kenya, because, well, you know, it was there. It's now the largest optical telescope in Kenya. What are we going to do with it? And the answer came by joining with the DARA program. I encourage you to go see the DARA stand with at the exhibition, Follow the Music. So it's DARA stands for Development in Africa with Radio Astronomy. And so they have a program that aims at developing high-tech skill using radio astronomy in 8 different African countries, mostly related to SKA. There for several training programs, and for the entire things, I'll encourage you to just go and check out the stand. Thank you. And one of them is a basic 8-week program in basic astronomy, radio astronomy, data reduction. And we use this telescope to add a 2 weeks optical astronomy module that's now given in Illoret. So this telescope was upgraded with a new dome for the project, so that it's better protected and it's going to last longer. And so we had a pilot school last year, and now we got some extra funding through the DARA project to run it 3 times a year for the next 3 years. So about 60 students a year will be trained in optical astronomy using that 40-centimeter telescope. In terms of the next step, we wanted to work towards a more permanent observatory in Kenya, because this is not the kind of telescope that can be made robotic or even operated remotely. but there are really, really good sites in Kenya, potentially. Cloud-free, very arid region. It's equatorial, so you have access to both northern and southern hemisphere, which is very interesting. And from the UK perspective, if you want to use it as a teaching telescope for at least part of the time, you actually, if you're east of the UK, which means that by the time students finish their day classes, you can actually start observing in Kenya and not have the students observe too late and be too tired for their classes the next day. So it's very ideal to share between, to collaborate between, let's say, African countries and UK for that regard. So we had several months of observation in our sat in Illarite to kind of characterize the site and the region. But as I said, it's not ideal site. It's very low. There's quite a lot of dust and quite a bit of wind as well. And so Graham gave a really good talk yesterday about doing site testing of different locations in Kenya. And they have identified quite a few from weather data, analysis of past weather data, a few potential good sites in Kenya, and particularly Oldonyonero and Mount Kenya. And so we're getting ready to install weather stations on these two sites to do more site testing over the coming years and identify the best possible site for this more permanent observatory. So that's the next step. Hopefully within the next few months, the weather stations will be on these two sites and starting to take data. And then the next step after that will be to look at well-designed foreign observatories and most importantly, funding and potentially new partners for the project to make that actually come true. So thank you very much, and please ask me questions for.
Thanks very much, Cyril. I just want to make a comment that it's amazing to see how this whole development in Kenya has progressed, because right at the beginning, there were Richard Vaughan, who's not an astronomer, was one of the people who, with Eddie and myself, thought, okay, we could do something in Kenya. And then just by, connections, networking with people, the UK became involved. Then I think it was Richard who got to know Richard Leakey and the whole Turkana Basin Institute. And Richard Leakey was very keen on promoting other science other than just paleoanthropology. So it's a great result, and really the future is very promising. But let me open the floor to questions, please. Yeah.
What research are you planning on doing with the telescope?
What research? I'll just repeat for the people online. What research are we planning to do with that telescope? Well, we don't have defined a research plan yet. I think for the teaching, we usually do very similar things to what we mentioned for the school, like a bit of variability, star clusters, probably, and things like that. But one of the things scientifically we're very interested in small bodies of the solar system. Colin and myself are working in small bodies of the solar system, and you can do a lot with a meter class, even half a meter to a meter class telescope in terms of small bodies of the solar system, because you have bodies that change very regularly. You need to be able to go on sky very quickly or spend a lot of time looking for change. So that's definitely one of the science cases we're considering, but we're not, let's say, stopping at considering other science cases.
Something I'd like to add.
Just wait for the mic, Richard.
Hi, sorry, Richard Vaughan here. One of the important uses for a telescope of this nature is not just for research, but to enable Kenyan students to get access, first-hand access at operating a telescope. At the moment, they have to fly out of the country to come to South Africa or far away, and many of them, of course, don't have the means to do that. So this is a way of slowing the brain drain and enabling Kenyans to have a facility on their own doorstep on which they can hone their skills before they travel to larger facilities elsewhere.
Thanks for that. I think we better move on to the next speaker, the last speaker of this session, to Brian Chaboya, a long-standing colleague of mine from SALT, who is, of course, going to talk about SALT.
All right, once again, thanks to the organizers for giving me this slot to talk a little bit about SALT. So I'm currently the chair of the SALT Board of Directors. So I thought I'd like to talk to you a little bit about sort of how SALT is governed. How do you have a large international collaboration successfully maintained for decades? And also a little bit about our plans for the future. So SALT was really started by people like David Buckley and Bob Stobie and Darrell O'Donoghue, who had this vision for a large telescope in South Africa. And early on, they were generating a lot of interest within South Africa, but they realized that really to build a large telescope, they needed international collaborations. And so they started to advertise the availability of this project. And early in the late 1990s, early 2000s, they really generated a lot of interest in the international community for building SALT. And this culminated in the formation of what's called the SALT Foundation, which is a private for-profit corporation that's in South Africa. So that's how SALT is formally governed. It's a for-profit because it turned out for various reasons they're related to taxes and stuff. It was the easiest way to import instruments and stuff like that into South Africa. And it's governed by a shareholders agreement, which was sort of a document which was negotiated between all the initial partners, and it sort of governs provided the overall governance structure to SALT ever since. And so I think that document's been very important in defining how SALT moves forward. And one of the key points was in the document was the formation of the SALT as a board of directors. And once again, each institutional shareholder was given basically, if you bought in at least a 3% level, you were given a membership on the board of directors. And so it's a very, in some sense, it's a very unequal board. South Africa initially put in like 34% of the funding, but they only got 2 board members. Other people put in 3% and got 1 board member, but that was an intentional choice was made, I think, to allow for a diversity of viewpoints in the board and to ensure that all the shareholders were invested in the future of the telescope long term. So the SALT board is the agency that's responsible really for the strategic direction of SALT and also very importantly, the funding of SALT. So when the SALT was initially set up, everyone sort of purchased shares, and that allowed us to have a physical item that we could tell we really are buying something. So in terms of generating interest within for example, within my own university, the fact that they were purchasing shares, they could understand that concept. They knew that they were getting some sort of asset that they could, and if they wanted to, at a future date, potentially sell. And so the idea of having a shareholding was well received by many institutional funding personnel. So the SALT board is, like I said, responsible for the strategic direction, but also for the fundraising and providing and approving the annual budget. And so that's really one of the keys for maintaining an observatory is having a sufficient funding to maintain the observatory long term. There's been a number of challenges with that funding model. Initially, the operations costs for SALT were underestimated by quite a bit, but and that led to some partners eventually having to drop out of the consortium. But fortunately, South Africa has been able to step in and increase their percentage of operations costs. And so early on, the decision was made by the SALT shareholders that we would not operate the telescope, but all the operations of the SALT telescope were delegated to the SAO. So the South African and SAO and SALT basically have signed a series of agreements, operations agreements, in order to allow SAO to operate the telescopes. And so SAO is responsible for all the operations, and there's actually very few SALT employees. All the employees basically are employed by SAO. So SALT has a chief financial officer who's a direct employee, but other than that, all the staff associated with the observatory are employees of the SAO. So very recently, the decision was made originally the SAO managing director was given the overall responsibility for managing SALT. And that worked, but it was always a bit of a challenge because the SAO managing director, as we heard, there's lots of things going on at SAO, not just SALT. And so the SAO managing director has a lot of things on their plate. And so we've decided that it makes sense to have a SALT observatory director, and we've implemented that recently with Carney, who talked yesterday, being the first SALT observatory director. So the SALT observatory director reports directly to the SALT board, but also reports to this SAO managing director. And that structure is something we're going forward with and seeing how that will work for us in the future. Within the SALT observatory director then is now responsible for all the operations of SALT, and also very importantly, I think, helping to develop and execute the strategic plan for SALT. So one of the things when you've built a large telescope, it's working, the question is, you can't remain stagnant. You want to keep improving it. You want to see what you can do next. And that's what really we're focusing on right now. I think one of the values of having a diverse board is seen in basically when you start considering what is the next step, or what do you want to do, how do you want to develop the telescope, there's really people come in with a variety of perspectives. You have a lot of different expertise, and that expertise and perspectives can allow for a broader consideration of what is the next challenges, what are the next steps we want to take with the telescope. And so, like I said, I think one of the advantages of being an international partnership is that we do have a lot of people with different expertise on the board, and we also have a lot of people with allow us and a lot of breadth of scientific interests, and that allows you to operate allows the board to have a range of opinions, a range of viewpoints that enable us to, I think, have in the end a very strong telescope model that allows us to keep, the telescope's been operating now for routine operations for close to 15 years now, and we're now considering what are the next steps we want to take. Okay, so the sort of next steps we sort of a slew of things have been in the development for a number of years, and a couple of them have come together very recently. So you already heard very briefly, we now have a near-infrared integral field spectrograph called NIRWALS. That's an image from one of the first light images from NIRWALS. So you're getting basically 212 fibers that are giving you infrared spectra up to 1.7 microns. Very recently as well, we've installed a laser frequency cone onto the high resolution spectrograph, and that will enable high precision radial velocity studies. Going forward, we heard already about the integral field fiber unit for the Robert Stobie spectrograph is a very versatile sort of low to medium resolution spectrograph that is been on the telescope from the get-go. It was originally built by the University of Wisconsin and Rutgers University, and it's been recently upgraded with this integral field fiber unit, which has a field of view very similar to the near infrared unit. But we're also planning to upgrade the CCDs in the near future, and we're also planning an upgrade, so basically becomes a dual beam spectrograph, which will double the wavelength coverage effectively you can get in a single observation. So these plans are well underway and have been moving forward. And in the future, we're considering a number of enhancements, both to basically the telescope top end, in particular ways to make the telescope more efficient. And that's one of the things the board is considering. And we also are eager to consider new instruments, but one of the reasons I came to this, one of the things that always when you're dealing with new capabilities and stuff like that is the funding question rises up. And so right now the current consortium is actively looking for people who are interested in wishing to contribute basically either to instrumentation efforts or in cash to these new potential new instruments or new developments at the telescope, the new top end. So we are currently actually, if you're interested, we make available, as we heard, this is called the Southern African Large Telescope. South Africa intentionally named it that way to show that it was available to African astronomers, and that's through the South African timeshare. But we also have a possibility, people have a possibility if they directly want to purchase time, they can purchase time. And as I said, we're also looking for people who are interested in pursuing opportunities to join the SALT partnership in the future, either as buying observing time or as, providing technical expertise or leading or assistant interest in instrumentation efforts. So the telescope, I think the governance, when you have a diverse board with the different viewpoints, there can be challenges, but it really leads, I think, to a system where because you do have a range of viewpoints, you really have a range, also have a range of expertise, and the board is able to consider a lot of different options and I think very thoughtfully develop a plan for the observatory long term. So we're currently, like I said, thinking seriously, what do we want to do about the sort of the next, we have a number of things coming online, but as a board, you want to think long term. And so what is really the next thing we want to do with the project, where we're going to get funding for the next project. And that's really where the board is thinking. And that's where I said, once again, welcome to international collaborations or any sort of interest from other people as well. So I think I'll just finish up now. Thank you.
Thanks very much, Brian. So questions? I want to put you in the hot seat and ask you, what are the big challenges? I mean, I know funding is one of them, but what do you see going forward for SALT in the next decade?
I think the funding is really the key issue. You know, big telescopes are expensive to operate, and particularly when you can't just let them lie stagnant. You want to develop new things for them. And so finding funding, particularly for new major instrumentations or major upgrades to the telescope, is really the challenge we're facing right now. And that's, you know, trying to figure out how to unlock additional funding has been a challenge for SALT for a long time, but we've been able to meet those challenges so far. But, you know, going forward, we now have somewhat, you know, things. The telescope is starting to age a little bit, so things are going to start to need to be replaced more, and so the need for additional funding is becoming more acute. And some of the current partners don't have that funding available to them. So there's been a change in the partnership over the years, as some partners have been unable to secure funding to maintain their operations of the costs. So I think that's really the real is to identify new. I think that for the board level, I mean, that's really the key.
Colin? Yeah, you mentioned you're looking at new instrumentation potentially. Do you have any particular kind of priorities or directions you want to go, or is that very much dependent on who comes with money and ideas?
Yeah, I mean, SALT we did do a strategic planning exercise, and one of the examples, one of the things we want to focus on is sort of time domain or transient astronomy. David has been very successful leading a program at SALT, and because SALT is a fully Q observed telescope with a very agile, easily changed between different observing modes, it's well suited to transient astronomy. We also are, like I said, we're developing this capability to do high precision radial velocities. So we're interested in potentially going into that area as well, basically exoplanetary research. And the other thing is sort of cosmic evolution. So these integral field fiber units is an expertise we're developing. And so you can imagine going to say much larger units and stuff like that in the future.
Phil.
Brian, just to take that last point you were making, emphasizing how SALT is totally Q scheduled, which makes it ideal for the transient program follow-up, coupled with the integral field units, makes it very efficient to do that. Now, at this meeting, we've been hearing about the forthcoming facilities, which will be generating vast numbers of transits requiring follow-up. Many of them are talking about the need for much greater levels of large aperture spectroscopic follow-up if you're really going to get that science out. And I can't help but feel that somehow we need to make the SALT option as a way. Let's face it, you can build the thing for $25 million for a 10-meter telescope. You should really be building 10 of those to cover all the things that LFST, Rubin, and other facilities are going to be producing in the next decade. This next decade has been called the decade of time domain astronomy, and SALT, with its aperture and focus on transient work, is a superb facility.
Yeah, I agree. I think that's really why we identified this as one of our strengths. And that's one of the reasons why, for example, one of the upgrades to the Robert Stobie spectrograph was to make a dual beam, so we had a much wider wavelength coverage, which was very helpful for transient studies.
Okay, let's call this session to an end and thank all the speakers. So please come back after the coffee break for the last 3 presentations. But importantly, also, we're going to have a discussion at the end of this FM1. So the SOC members will be up here and it'll really be sort of an open floor to bring up some discussions that might follow from some of the presentations over the last 2 days. Thanks.
yeah. So now it's working. Okay, it's the reverse. I mean, this is counterintuitive. Okay, so let's start the last session of this focus meeting. And the first speaker of this last session is Suir Benghaldun. Please. We have to wait until they put the view graphs before you start operating. Now you can start.
Yes, thank you very much. First of all, I would like to apologize for missing the first session because of delay of my plane. But thanks to David and Mirjana, and they managed quickly to arrange this. I will speak about Okeimdon Observatory. Most of you know very well the history, I think, of this observatory, but I will go fast. We are Okeimdon Observatory. There is no laser. Yes, Morocco is here. Okeimdon Observatory is in the south of Marrakech, and you know the famous TRAPPIST telescope, who discovered the system TRAPPIST. I will speak about that in my slide. This picture is from TRAPPIST telescope. We are a small group in Morocco of researchers in astronomy, and mainly in laboratory who called High Energy and Astrophysics Laboratory. We are two groups, one theoretical groups, High Energy and Theory, and the second is Astronomy and Astrophysics. We are about 25, plus than 25 members with some graduate study, and this laboratory managed to Okeimdon Observatory, who is located at 75 kilometers in the mountain in the south of Marrakech. This slide is just to show the evolution of the observatory and generally in the astrophysics in Morocco by the impressive increase of yes, but by the impressive increase of the publication, the paper, and also the citation of this paper in the main astrophysical journal. And also you can notice all the curve is growing rapidly this last years for the Moroccan researchers in astronomy. This can be done thanks to the international cooperation, diversification of cooperation we have in all the continents, and a lot of colleagues from Europe, of course, but also from Korea, from Chile, from Canada now also. We try to be involved in African astronomy emergence, and we are part of Africa initiative of for planetary science. Yes, called AFIPS, that we create with our colleague David Baratou from IRD in France. We also try to make some cooperation between Europe and Africa by submitting proposal for financial. Up to now, we don't get a success with this proposal, but we hope we can have it in the next phase. This is a brief view of Camden Observatory. We now have 6 domes with the small telescope between 30 centimeter and 40 and 16 centimeter. And in the next month, we will have one of 18 centimeter. The main tower is here with this dome, and inside the dome we have a spectrometer, and we study variable stars. And our colleague Ben Hida will talk about that in the focus meeting 10, I think, next week. We have also some camera for meteor and also for monitoring the dark sky. We have famous MOST telescope who make a lot of discovery in the observatory with our colleagues from France and Switzerland. We have meteor camera too. We try to build a network of camera in Morocco, the network called MOFID, and 2 cameras from this network is located at the observatory. We also involved in space weather, thanks mainly to cooperation with our colleagues from Illinois, who monitor an experience called Renoir to monitor disturbance of high atmosphere and especially ionosphere. Let's see. This is also a cooperation with Saudi Arabia, who installed telescope in the observatory, and with Korean from Space Korean Agency. They also put a telescope to observe mainly satellite and satellite debris. And we have the TRAPPIST telescope I already speak about. And with this telescope, we participate to famous TRAPPIST-1 system discovery. With the TRAPPIST, we do also a program of comet, and our colleague here, specialist of comet, Youssef Moulin, can speak about that in the symposium 393 next week. Yes, last years we have a success with one projects to put together professional astronomer and amateur astronomer, and we can do that 3 years ago now with Moroccan photographers who put the observatory in Morocco. This is first one. And now we have 3 locations of this group who observe with us some scientific target. If, of course, they do photograph, nice photography from the deep sky, but also they help us to make observation for exoplanet now and for some transitions event in general. You can see here the James Webb Space Telescope passing across the sky of Morocco and catched by one of the telescopes of this group. We organized at the observatory several training and mainly with our colleague, of course, from Belgium, who set up a TRAPPIST telescope. And each year, the master students come to Morocco and make observation with this telescope and training. As you can see, here there is a conference room in the observatory when we can do this thing of training. Yes, this is a brief history of the observatory. We can come back. We started our journey at 1984. By setting up first laboratory in the research center in Morocco, and move after that to Marrakesh, to Qadiyat University. Set up several instruments, and I don't have time to go deep in all the step we have. But of course, we can have a discussion with apart with you if you want to know more about the evolution of Okeimdenas Observatory. Okay, this is some with spotlight. Important dates for the observatory. We, of course, in the context of this focus meeting, the success of observatory come from first the good site testing we have done, and the publication we can, scientific publication we can to have about the astroclimatic parameter we have the observatory. After that, we catch the attention of our colleagues from astronomical community and come to ask us to put telescope and to use observatory for several program. And after that, the Morocco is selected as one of the potential sites for extremely large telescope, ELT. And we do this campaign and select one of the mountains, not at Okeimdenas Observatory, because we need to have a mountain free of light pollution and far from people and habitation. We choose Jebel Aklim, and also with the cooperation with our colleague from Nice University, and in the framework of ELT site testing group, we do the qualification of this site. We also get instrumental expertise, and yes, this is the observatory, Okeimdenas Observatory, some years ago. We installed the first experiment about helioseismology, and thanks to this first experience, we can to put our first site testing, which is very simple instruments based on just 3 photometer with 3 filters to monitor the statistics of number of observable nights and also of extinction. We have atmospheric extinction we have at the observatory. We this experience, this instrument will followed by our colleagues from Tucson University who set up the GONG Global Oscillation Network group and also made site testing for this for the network using pyroheliometer, and they set up one of this pyroheliometer at the Camden Observatory. Yes, we made a lot of work to qualify the site in terms also of dynamic turbulence, and we published a lot of paper on this area using one of the instruments we set up ourselves at the laboratory. This is a differential image monitor, but we develop our own for this instrument, and we use it for several times to make site testing in Morocco. And this is main publication we have present in the quality of Camden seat. We can go to this publication and so more. With this work, we had yes, some thesis on these topics, and PhD student become a laboratory afterward. We organized with the Astronomical Union one famous work to 2000, and we had success for that. We help us to be elected for ELT testing project I presented. I don't have a lot of time. We do work to in the prospection first to select the sites in terms of wind circulation and orographic position. And after, thanks to Moroccan army, we can put instruments on the top of the mountain, because there is no road to access this site. And site testing with several interesting results. We can, yes, I pass very fast the achievements we have, thanks to the expertise our group, acquire in this topics. We can develop some instruments like ESS, SSS, single star SIDAR, for monitoring the seeing and the astroparametric astroclimatic parameter. Here you can also see one important achievement in our laboratory about the isopistonic angle. And thanks to our one work in doctorate, we can develop the method to monitor this parameter. Okay. Yes. I will pass in review some important telescope we have and the program we developed. It is MOSS observatory I already speak about. Thanks to this telescope, we made a lot of discovery of comets. We have some statistics here. You can see we have 4 comets discovered at the observatory, and up to now 11 near Earth asteroids, as you can see here. And we send several observations to Minor Planet Center And as you see, the Oakhamden Observatory is ranked 7 among big telescope and discovery of this near-Earth objects. This is comet named Oakhamden, and I will also quickly speak about AOL, which is a network of telescopes set up by Korean agency, space agency, and also the importance we can retain from this, that all this telescope is set up in a remote mode, and our partner can access to the telescope and monitor this telescope, of course, and made some measurements. This is a publication we have, a communication I have made about this at the 2015 in the Iau General Assembly too. We are involved in space weather too, thanks to this experience I already speak about with the University of Illinois, with Jonathan Makela as PI of this Renoir experiment we set up at the observatory, and thanks to that we can monitor the sky of Oakhamden, and we can get the afterglow and the velocity of ionospheric disturbance. We made some publication in these topics with this cooperation, and of course I will come back in the symposia 3993 next week to speak about exoplanets and about TRAPPIST and the famous discovery of TRAPPIST-1 system. Yes. Yes, here I choose to see you some recent significant discovery where we participate at the observatory with our colleague, of course, and we had 5 publications in Nature and Nature Astronomy. Now 6 publications up to now. Yes, we can go deeper in the detail of all of this, but the objective is to show you that even with the small telescope in the good observatory, we can do efficient observation and get involved in important publication. This is about blue Walker 3. We catched at the Oakhamden Observatory. Yes, here, and we published this in Nature too. This is the first time we can observe in detail the most polluted sky pollution with this. Yes, as a conclusion, we can say that the Oakhamden Observatory has propelled to the forefront of scientific interest due to its exceptional location first, and the best astronomical side cooperation around the world. Yes, this thanks to exceptional conditions we have also in the site. And this surge of interest has provided us with an opportunity to cultivate research and training within our group in a growing team. And now Morocco, we can say, occupies a prominent position in the region, Africa and Middle East, in terms of scientific publication in astronomy and astrophysics. Furthermore, the success story of Oakhamden Observatory underscores the continued necessity of investigating in small ground observatory, particularly in a region of the world facing economic challenge. That what is the case in Africa, of course, And I think our colleagues from Africa can have inspiration from the history of Camden Observatory to build, develop several observatories like that around Africa. We are already in cooperation with our colleague from Egypt for developing their next big telescope, and I hope we can have opportunity to have other African country involved in this wake up of astronomy in Africa in our continent. Thank you so much. Yes, we can just say the, yeah.
Let's just make one quick question. Questions? Yes.
Thank you, Zuhair, for your presentation. I want to ask if you have a local legislation to protect your site from light pollution and urban extension. Do you have any local legislation to protect your yeah, like a law that protect your site from urban extension and light pollution?
If you have, you
if,
mean
if there are laws, if there are laws that protect the sky.
If you are lost,
no law
legislation like
قوانين
يعني قوانين بتحمي المكان من ال ان هو يحصل فيه امتداد عمراني او لايت بولوشن يأثر عليه.
okay.
قوانين يعني عندكم في
Okay, not yes. For the Camden Observatory, we have surrounding some village and population, but we selected sites we have done for ACLIM. If we have a big project like the projects you are running to have to Camden, we will do it at the ACLIM site, which is far from the population in the village than Camden. But we don't have any study to. We don't make that. We don't have a specialist to tell us how can we grow. But as you know, we are setting up projects to protect the area of in Atlas, so that we can make some regulation beside Moroccan opportunity to protect this area from light pollution.
Okay, thank you. Let's thank our speaker again. And we're moving to our next speaker, Solomon Tessima, please. So please wait until the technician tells us that we are good to go. Yeah. Solomon, you can start now. Oh.
Okay. This is to show the overview of the Lalibela or Abu Nassif astronomical project. And lately, first, I will somehow to highlight what is. Any problem? Maybe.
Window solved now. Yeah, we can go ahead. 1 minute.
Okay. Okay. Okay, first of all, let me start from the, I think, really, astronomy research infrastructure in Ethiopia mainly emerges after the establishment of Ntoto Observatory and Research Center in around 2014, and that Ntoto Observatory is situated in nearly 3,150 meters at the outskirts of Addis Ababa, the northern part of Addis Ababa. And then the interest of the many of the universities and the government really pushes to have another astronomical site and outside of Addis Ababa. And because the Addis is always expanding, and in order to have another to have another facility in the northern part, then this and this consists the facility consists of the Ntoto, that is visiting centers, accommodation of students, lectures, rooms, and also IT and science operation begins in early 20. Now it is already more expanded, the observatory. And finally, it was commissioned nearly late of 2015 and has been planned to expand another center around Mount Lalibela Mountain, Abu Yusuf. And it was two sites parallelly. The first one was after the Ntoto. This is maybe an Ntoto site, and David was really South Africans, especially David, was devoted to support and also to really from the scratch to the commissioning of the observatory, Ntoto Observatory. And the main science was in the Ntoto is rapidly follow up all these sciences expected to be extrasolar planets and rapid follow-up observations, detection of extraplanets, and as well as also targeting opportunity for multi-wavelength observation, X-ray, binaries, and time series photometries, pulsating, and high time speed and search for, and mainly that is depending on the capacity building and training of expertise. That was, and so far we trained more than 22 PhD students and 35 master's students since 214 up to now. And our main talk, my main talk is potential sites. Then Ethiopia's geography and the topography is really different in nature. From lowland to highlands and different situation, different climates, and so on. Then expected areas of astronomical sites is really mainly to the northern and northwestern part of Ethiopia is highly expected. Then this is some of the areas of Ethiopia that's already protected by the Ministry of Tourism and preliminary identified by the master's students. These are the pointers already. Some of the pointers, these pointers are potentially identified sites for astronomical observations. Then this is done by the master students, and then one of the main important parties is the Abu Naisef, and two areas in the Abu Naisef means in the northern part of Ethiopia, and located 4,260 meters, and it is a highland and also one of the highest mountain, and because our political division is like regional status and Amhara regional state. Then the place was mainly conducted in many people are, it is one of the best tourist area and many of the conducted the nature and diversity of that place. And the area is already, it is a park and dedicated only approved by the 2030 by the regional government for astronomy and also to the local environment. Then there is no any other disruption. And it is about 50 kilometers from the Lalibela city. And it is at the mountain, nearly 50 kilometers. It was two places. One is the Abu Naisef and the other one was Abu Gara. But my focus is here. This is the mountain already. This is Abu Naisef mountain, and in the northern part, and already abandoned and covered by. There is no any light pollution and sparsely populated, because it will not be a good area for farmers and for other issues. Then the current status is, you see, the site testing was started in the 2014, but interrupted in different conditions, and mainly in 2016 and 2017, it was conducted continuously. And this is the construction already for the researchers and for the engineers to be stayed there. And the project is financed, this project is financed by the universities and also regional government. Regional government covered the land, that is the road and also electricity, and at the same time also the universities expenses covered by the running cost, and others are by the consortium of universities, and also there is astronomical, that is Space Society. And the instruments quality parameters related to the darkness and pollution effect, all the instruments were deployed. And there is one of the, I took from the data of indicators that in 16 million 1 years of seeing data with more than 76%, a total number of 90s to be taken have been recorded from 2016 to from January to December 2019 are analyzed as shown, whether the testing site is suitable for optical astronomy or not. Then the dim seeing preliminary measures have been analyzed. Then the medium of dim seeing is more or less ranges from 0.48 to 0.89, and then almost 64% nearly, and to 99% of the dim seeing values are less than 1%, And the dim seeing measurements for the year of 2016 shows about 77% of the dim values are less than 1. That means the median of the dim seeing have been calculated and 0.73, and extremely good seeing values have been recorded with the base values of at approximately 0.3. This is taken from that only for the 2016 data. Then here the seeing values are very promising to consider Abu Naisef sites as a potential area for hosting future astronomical observation, where vast quantities of astronomical data should be measured again. And because of some challenges of the last 2 years at northern part, then currently the site testing is not being conducted because interrupted because of some conflicts. Then there are challenges in the northern part, some conflicts, and still the financing system is more required, and the lack of the professionals. And all the equipment, some of the equipments were ready, deployed to Addis, and also waiting for really fully to the next piece. And our future plan is restarting the interrupted site testing, deploying additional instruments and engineers to the site, and employment of professionals again to the engineers, and giving the short trainings, and more collaboration is required, because currently almost 8 universities were involved into the consortium and ready to additional financing, but collaboration for especially to the Africans and other international communities the most important. And summary, the Abu Naisef is really a good opportunity, an excellent opportunity for astronomy, observational astronomy with diverse weather conditions. And Ethiopia's consortium universities are committed to finance the project, and I encourage all us to collaborate and work together. Thank you very much.
Questions, please? Let's wait for the microphone. Yes, here.
Thanks, Solomon, for your good talk. And I want to ask if you have an expectation of how many clear nights you have in this mountain, because I can see that the mountain is full of green land. That means that there are a lot of rains. I don't know if the clear nights are high or low, or do you have an expectation of how many clear nights do you have during the year?
From the preliminary, taking from the meteorological preliminary data, then and at the same time also from the nature of the environment, then it is expected to be up to 230 to 245.
There is a season for rains, for example, during certain months?
Yes, there is rainy season, but like, because in the rainy season in Ethiopia, in the central and in the northern part, in the southern part, of course, the rainy season is much. But in the northern part of, that is Abu Naisef and others, the northern part, it is more or less dry and less rainy season.
Thank you.
More questions? I would like to ask for how long, ideally, you will do the site testing before taking a decision on the site?
Our plan was really to finalize continuously to the 3 years of taking the data. And that was, if there is no any challenging problem was not be faced in some conflict, then our plan was to finalize the preliminary, that is the data of site testing, and to continue to the other. Anyhow, the plan is 3 years.
More questions? Not, let's just give another applause to our speaker. And we move to the final talk of the session, but Iau Ga. Are we
big
good?
green button, right?
Are we good to start? Okay, let's start.
Good afternoon, everyone. Thanks for inviting me. So what do we think
what do we mean by democratization of astronomical research? We mean astronomy for everyone, so that wherever you are, that you can do cutting-edge astronomy, research, and education. Take my personal example. In very short time, I plan to partially retire to a very small country that I'm from, to a very small island and a small house with a small study room. But I plan to do big science. How will I do that from my small study room? I will do that with LSST data. And everyone will be able to do that around the world. And so the point of this talk is to briefly show you what Rubin and LSST are about, and just to showcase a few of the tools that you will be able to access in about a year from now and start accessing LSST data. So just to get some terminology straight, Rubin Observatory is an observatory in Chile that is about to be completed. And the first project, the first sky survey that that observatory will undertake is called Legacy Survey of Space and Time. So that's project, it will last for a while, but the Rubin Observatory will probably last much longer than 10 years. As you can see in our mission statement, we want to produce an unprecedented astronomical data set. And we want to make it widely accessible to a diverse community of scientists all around the world. And also we want to engage public all around the world. So I'll spend about half of my time to briefly tell you what Rubin and LSST are about and where do we stand with the construction of the observatory. And then I'll spend the next half of my presentation show you some of the tools that already exist. And they will be the tools that anyone around the world will be able to use to do astronomical research and astronomical outreach. Rubin is not very large telescope. This is Rubin compared to some of the largest telescopes being built and to two space telescopes. What is unique about Rubin Observatory is the product of the mirror size and its field of view. This is the quantity that determines how fast you can scan the sky. And with Rubin, we will be able to scan the sky 100 times faster than any comparable telescope like Gemini South and North, like VLTs, etc. Any 8 to 10 meter class telescope, Rubin will be 100 times faster. So LSST that we budget 10 years for would take 1,000 years on any other similar telescope. And this is Vera Rubin, famous for dark matter studies that observatory is named after. So from the technological point of view, the trade secret of Rubin Observatory is its large field of view. You can see comparison here. At the top right is typical field of view of those dozen or so 10 meter class telescopes in the world. Bottom right is field of view for Rubin Observatory for Simone Survey Telescope and LSST camera. So it's 3.5 degrees across. It's giant, about 100 times larger than other fields of view. We will be using filter set that is very similar to SDSS, except that SDSS Z band was split into two bands, Z band, still called Z band, and Y band. And that was done to improve sensitivity to very high redshift objects around redshift of 7. There will be no time allocation committee for Rubin Observatory. There will be one single data set that will serve 4 different science programs: cosmology, time domain science, Milky Way structure studies, and solar system studies. And here you can see how the scheduler, the brains of our observatory that are running, that are computing cost function. You lose time when you slew, you gain something when you get certain signal to noise. You take into account observations, etc. This is how it will be run for 10 years. It won't be astronomers putzing around sky, but there will be essentially AI, artificial intelligence program that will observe for 10 years. The data will be much deeper than existing all sky surveys. This is example from SDSS. This image goes to about 22nd magnitude. And SDSS covered about 1/4 of the sky, the depth. Gaia, for example, that has the whole sky coverage, is about 2 magnitudes shallower than this image. With LSST, we'll go about 3 magnitudes deeper than SDSS for each image. And then when we
co-ed hundreds of images will go 5 magnitudes deeper than SDSS. The same part of the sky that you see here, it's a teeny tiny part of the sky, 1/10 of the full moon's diameter. This is how it will look with LSST. This is what 5 magnitudes of depth bring you, many more objects. And for that reason, LSST catalogs will include about 20 billion, with B, 20 billion galaxies and a similar number of stars. That will be the first time in the history of astronomy that we will have cataloged more objects on the sky than there are living people on Earth. Literally, you could name a star and a galaxy after every living person on Earth, and many dead ones too. So it's not just about getting the data. The goal of Rubin Observatory is also to process the data to what we call science-ready stage. So instead of having a raw image coming out of the camera with observational artifacts in pixel space with electron counts, what you will get is properly astrometrically calibrated image and flux calibrated in Janskis. Not only that you will get calibrated images, but our software pipelines will go through those images. They will detect objects, measure their properties, and produce catalogs so that not everyone has to do this same step. And finally, not only that we'll produce catalogs, we will deliver them to you using easy-to-use tools that will enable people around the world, including retired me, to do remote science with those tools. So our data management system is quite exquisite undertaking. It costs as much as the camera itself or the telescope and observatory itself, well over $100 million. We have close to 100 people that have been working for over a decade on these products. So obviously I can't do it justice in 10 minutes, but there will be 2 different flavors of data products, yearly data releases to do static science. And then we'll have real-time processing where each image that we'll be taking in Chile will be transferred to our processing data center in California at SLAC. It will be subtracted from the average of previous images of that part of the sky to get what we call difference image. And then objects in that difference image, all objects that either change in position or brightness will be measured and reported to a data stream publicly available through internet within 60 seconds of closing the shutter in Chile. It will go everywhere. And that's particularly important when you want to look for objects that are rapidly changing. Here is an example. You have image 1 and image 2. You subtract the 2, and if nothing changed on the sky, you get sky noise in the background. But in the bottom row, there is a new object in image 2, and we will detect it in difference image and alert you within 60 seconds. And then you can take your beautiful telescopes and follow up and do whatever your particular science will require from you. So where do we stand with the construction? The top row shows 3 computer-generated images of the project decade or 2 decades ago. And the bottom row are photographs of the real thing. Rubin Observatory is real, and soon it will start operating. Okay, I skipped the movie. There is a little clip of our telescope mount assembly moving very fast. We just last week installed secondary mirror. We are about to put in commissioning camera. Within few weeks, we'll install primary tertiary mirror, and sometime in September, we will get first images of the sky with our commissioning camera, which looks from the outside just like this one. This is LSST camera. From inside, instead of 189 sensors, it only has 9 sensors. But in January of the next year, this camera with full focal plane will start getting images too. That's the entrance lens to our camera. This is just to demonstrate how large that camera is. This is the largest camera ever produced. It's in the Guinness Book of Records, and this lens is the largest lens ever produced. It's bigger than the lens on the Yerkes Observatory. This is the camera when it was fully assembled just before shipping to Chile in May of this year. This is a photograph of the focal plane. There are 189 science sensors, each 4K by 4K. And then there are additional 12 sensors for controlling focus and for doing active optic system. This is pupil image of an old photograph of Vera Rubin, which shows that the camera is operational, that out of 3,024 amplifiers, each CCD has 16 amplifiers to enable 2-second readout. It's 3.2 gigapixel camera, but the readout time is 2.4 seconds. So all but 3 are operational. This is 2 months old image from the summit, from the observatory. This is the camera. It arrived to the summit in May, and now it's being again tested. How's that?
You have 1 minute left.
I have 1 minute left. Oh no. So these are the dates. So LSST starts here from now. Lots of data. This is the point of the talk. Rubin Science Platform, an amazing tool that will allow everyone in the world to access the data. Words, more words. There will be 3 components to Rubin Science Platform: portal, notebooks, and APIs. Portal is for interactive analysis of our catalogs. You can choose your favorite object, favorite little point on the sky, and you can play with it, or you can select with SQL query something on the sky, play with it. You can do fun stuff with modern plotting tools that do not choke when you have billion objects. So you can choose your objects, sub-select, choose area on the sky, plot color magnitude diagrams, etc. Notebooks, even more powerful. That's for doing really cutting-edge science. It's Python notebooks that talk directly to our data. You do not have to download 60 petabytes of data. You go to a small house with small study room, you have a laptop, you connect to Rubin Science Platform, and you run computers at Slack in California. And so not only that there is code, there are lots of documentation that you can use to learn how to do it. Even people over 60 can learn it. My PhD advisor, they retired, learned Python from scratch, and now is enjoying his retirement. This is an example of how to analyze data, how to display images. On the left, you can see this 01, 02, 03. This is just part of the example notebooks. You are not thrown to this tool without help. You don't have to fear it. You have notebooks that are examples. You have extensive documentation. You can do fun stuff with it. This is example of give me all the images that simulated data set includes at a given point on the sky. Then there are more tutorials, etc. It's fantastic even for teaching a class in astronomy, for attracting students to astronomy by giving them access to real data. If they look at images, there is high probability they will be first human eyes that ever looked at that image. And the tools are modern. They can do billions of objects. They're intelligent enough. As I told you, it was a major software project. We burned lots of money to make excellent products. And so you can then play all kinds of games. There is community forum where you can ask questions. We have over 1,000 users already. We are thinking we'll have about 10,000 users, good fraction of all astronomers in the world, once we go on sky in about a year from now. So all what you need to do is to have good internet connection, imagination, and knowledge, and you're good to go. Thank you.
Questions, please?
It's a nice talk. I can second the Rubin Science Platform is great. Just a quick question clarification. Are there institutional limitations to accessing the Rubin Science Platform?
Our science platform is designed to enable access by all data right holders, which includes anyone in the US and Chile, plus a very long list of several hundred institutions from around 40 countries around the world. And after 2 years, the data access will not be open to everyone, but the data itself will be public. And so now there are about a dozen institutions in the world that are planning to clone science platform and then enable other people to access data. Then, of course, this alert within 60 seconds, that's fully open to everyone. And education and public outreach materials are fully open to everyone right away.
Great, thank you.
Johan?
Johan Knappen, thank you. How can new users be trained and can they be mentored?
Yes, thank you very much. This is an excellent question. We already had a few workshops where people are trained, and the idea is that more people we train, the more trainers we'll have. So people who went through training now are training other people at their home institutions. All these sessions are recorded and available for free on our websites. And then all these notebooks, they are available. And all the other documentation, including software, everything is open source that we produce in Rubin Observatory. It's completely open source.
Okay, thank you very much. Let's thank our speaker. And I'm going to invite the Scientific Organizing Committee to please come forward. And we are going to just have a discussion with all of you about this and the past sessions.
No, Solomon wasn't on the SOC, just the SOC. Yeah. So we're all members of the SOC, which was actually a larger group. I said to Yosri, who's the chair, would he like to speak? And he said, no, you can. So this is just an opportunity, rather than that we just leave the meeting after all these talks that we've had for the last 2 days, to give an opportunity for people to feedback or for people to make comments and maybe to think about the future. So we've heard a lot in these last 2 days about all of the facilities, about the plans for us to expand research in Africa, and in particular, some of the big missions like Jelko's just mentioned, the huge opportunities with Rubin. So really the floor is open, and yeah, we'll just take it from you guys. Please don't hold back for comments. I don't think we really want it to be questions, say, pertaining to talks in particular, but if you think it's relevant to do that, then feel free to do that. And yeah, so if the people with the mics.
I have one, so.
Oh, okay, thanks, Itzia. So yeah, Dominic, do you want to start?
Yeah. So given that you mentioned the facilities, what do we do with and for the people?
Yes, my comment was about facilities too, and I actually just tapped someone on the back of the shoulder today and asked them, "Is there an African Journal of Astronomy?" And I was told there isn't, but there's a monthly notice of the South Africa. What is it? What is it, David? Something related to South Africa.
Monthly notices of the South African.
Yeah, don't be. I think in the case of Africa, don't be beholden to European and.
Yeah, it's more of an amateur journal, actually. But there has been discussions within AFAS. Maybe Mariana might want to say something about that.
Go ahead, David.
Well, so there are some discussions about a journal for access, which I think there's a local. An African journal, but it comes with its issues. So, of course, we want to publish in reputable, high-impact journals. And so there's always that worry that if you have a journal that is not sort of sufficient impact, that people might not want to publish in that journal. Yeah. And that's also, it ties into like, open access for journals. How much do you have to pay as an author now? And many journals have moved away from no page charges to open access and therefore page charges. And that's a big challenge in Africa because the page charges just become unaffordable, which is why this conversation has begun.
Yeah, well, that's really my point, is that I would say to African astronomy, don't be beholden to these big journals and so on. You can make your own impact factor. To be honest, it's if you're not steering the ship, if you're down in the hold, you can't direct your future. You've got to be up there, on the bridge, directing your own future, and self-determination is key. So I think don't be over persuaded by high impact factors, because impact factors rise and fall. And I know many journals that are on the up and rise. You just need a good editor, you need a good editorial board. And if it comes together as a coherent entity in Africa, well, in terms of impact factors, if you're referencing and citing one another, you're going to get a higher impact factor simply as a result of doing that. So break new ground. Don't be held back by tradition too much in publishing, certainly.
Yeah, I understand that sentiment. On the other hand, I have seen the emergence of journals that are poorly refereed, and publishing in those, I think, is a mistake. I don't want us to go down that route personally.
Yes, I mean, just to add a bit, I mean, currently, I think it's only astronomy and astrophysics that is allowing the majority of African countries, but not all. Like the northern part is excluded, South Africa is excluded from payment, but the rest of sub-Saharan Africa is free of charge. And that's the only option that we are currently left. As David mentioned, there are plans under the Science Committee of AFAS to start with the journal, but that will definitely take time. And then it will take time also once the journal start to actually come up with a certain impact factor. And I agree with you. I mean, we should have big goals, but then we have to also think about students, because for us, I mean, if we publish now in, of course it matters, but for the students who are just starting their career, PhD students, they do need, for then later on getting, grant scholarships and so on, they do need to publish in first impact in Q1 journals. So it is really frustrating that we as, more senior are asked to review journals, I mean, review papers, we do it for free. And then our students are asked, to pay for the journal, 100 euros or pounds per page, so it's absolutely frustrating, and it's totally unfair, and it's something that it's the whole community that should work together on changing that. I don't think African countries are the only one that suffered that.
So this is getting animated. So I am going to give preference to the panelists, and then I'm going to just to take turns for the rest of people. Please go ahead.
No, just to say that we don't have a lot of time, and if we can back to the topics of our meeting.
Well, before we go to the next topic, I think all of this is valid, by the way, because you're just securing how to make an impact.
It's not the right place.
And before we go to the next topic, I want to just comment on that one. I think it's great if you create an African journal, but coming from also the South, I think the Latin American community will be more than delighted that the Africans submit to the Revista Mexicana de Astronomía y Astrofísica, which is free of charge and is in Q2. So it's going there, and now I'm coming here.
Okay, I will back to the topic, and thank you for the SOC for organizing this this focus meeting about this ground-based telescopes. And I think it's a very interesting point to have that. And I think this is a good point not to start, but to continue what we have been doing. And as I can say, Morocco is one of the examples that Zuhair has presented, that we started with ground telescope. But in the same time, we should also think big, as Zilsu mentioned, and they would like to back to him about your strategy of the inclusivity. Are you thinking to providing some trainings towards to African continents, which I don't think so. There's some of the institutions are in the consortium.
Would you like to reply to that quickly?
Was that question or a comment? We do have participation in our in-kind part, international part of the observatory from South Africa. I believe there is also one person from Egypt who is in that group, but I'm not 100% sure. But we definitely have a lot of people from South Africa from their observatory already participating. And we basically do have training sessions that if there was some local organization of African institutions, like in Morocco, for example, and then delegates come and we have maybe 20, 30, 40 people, we could talk about sending then one of our team members who could give training 1 day, 2 days, 3 days. That's totally doable. Just contact us.
And we're coming back. Let's just keep the order.
Yeah, following up on what Eddie has just said, I'm not sure that we have to worry about a journal per se, but two things I've learned from the last couple of days. First, we must not think in silos. And secondly, the meter and half-meter telescopes can make a serious contribution. So what I'd like to suggest is that after this conference, we set up some kind of portal where we can exchange ideas. As with every other walk of life, intra-African trade is pitifully underdeveloped. And this conference gives us an opportunity to develop ideas together, whether we're in Kenya, South Africa, Morocco, or Egypt. We need to develop our facilities in conjunction with ideas that are being developed elsewhere on the continent. So I'd like to suggest if we could develop some kind of forum, internet forum, through which we can exchange ideas and share our ambitions, that would help to accelerate the progress of astronomical development on the continent.
Will the panelists like to comment while I go to the other
Yeah,
part
well,
of the
I
room?
guess I should comment the fact that the African Astronomical Society has such a portal. And so that would be the obvious mechanism to take that forward.
But it is still in developing phase. I mean, there is the idea of the portal to cover not only the science part, also the outreach, education, like different aspects, but it is still in the developing phase. So, I mean, we should definitely speed up with that, because the idea of the portal came basically since we started, with all the committees. So it's been there for quite some time, but I mean, the number of people is very limited even under the secretariat. So the things not always go with the pace that we would like to see, no? But I mean, it's a great idea. I fully agree that we should, from this session, come up with something that gives some sort of result. And I think the small observatories that we have across Africa, many of the observatories face similar challenges, difficulties, especially when we come also to the part of the protection of the sky and so on. So definitely we do need to work more on bringing the efforts together. And so having somewhere where we can continuously communicate it will be really useful. Yeah. So we will definitely keep that in mind.
And I think the fact that also there'll be proceedings from this focus meeting where people who have presented here will have the opportunity to put these in as a paper. And maybe it behoves the SOC to write a sort of conclusions about what came out of this meeting and recommendations for going forward. Yeah.
Okay. Let me comment. Thank you. First of all, I think this is a very important endpoint and crucial really for us. Then in order to come to attention to the main topic is how we are going to collaborate. What will be the mechanisms? These are very important. The first one is human capacity. That is training of Africans. We have to set the platform how to build the capacity in astronomy, engineers, and observational and theoretical astronomers. This is very important. The second one is the number of people is increasing from time to population is increasing from time to time. This is, I hope after 10 or 20 years, then securing astronomical place or site may be a challenge. Then that is, we have to create a strategy even to secure sites at the same time also, and legislation to secure the society is also another important thing. That is, dark sky is a challenge, and also in many African countries there is a small observatory, but the challenge is human capacity, the expertise in the dark sky, and at the same time, urbanization is also another issue. So these are very important if you can bring and discuss together. And exchange of how for the development of astronomy in Ethiopia, we know how the effort of South Africans are assisted us, and especially Petri and David and others. Then the same thing, others can assist and exchange each other. That can be an important if you really to come together. Otherwise, proceeding and continues as usual may not be make a very strong astronomy in Africa. Thank you very much.
Any comments?
Yeah, I think that your point is very important. So, and I think that the exchange and information and the exchange of people is very important to develop the, how to say, the real collaboration inside the African continent. So, but I recommend that. So maybe you should start from the small step. Okay, so and he pointed out that some kind of forum about the information exchange between the each observatories. So such kind of activity is very important, and I think that's very appropriate to start to develop a real collaboration and a real exchange. So and also and I don't know, but it is difficult or not for the African countries, but it is very good to exchange students between institutes to institutes. So you can you do that? So maybe but universities, so different countries universities send that students. Or they accept the students or something like that. That is very important to how to say grown up the students expertise. Yeah, that's my thought. Okay.
I would agree with that, and I think there's an example set by the fact that South Africa has had students from other places in Africa come to do studies and finish PhDs. And, you know, anecdotally, they go back to, I mean, many of them go overseas, but many of them go back to their own countries and they begin astronomy groups. And that's been sort of quite successful in a number of countries in Africa. But if it became a wider thing of international, you know, having students go to the US or to Europe or Japan, then it would clearly foster that and grow the communities back in Africa.
So my name is Darren Norman, and I'm the current, I just started as the president of the American Astronomical Society. I just wanted to thank the organizers because this was really, really useful, interesting, and I learned a lot of things about astronomy in Africa that I didn't know anything about. I knew a lot about the radio work in Africa, but not about all of the folks doing optical observations in Africa. So I want to thank you for that. I also just wanted to mention that, in fact, the American Astronomical Society, we publish our own journals. And in fact, we have a waiver program. It's actually underutilized. And so as you submit, you should ask about it if publishing is, if it's an obstacle, the money is an obstacle.
Thanks for that.
I can tell from around the world, publishing is becoming an obstacle for more and more countries. So definitely.
Yes.
Any comments?
Well, I think, I mean, just to come back maybe to the last point regarding the trainings and collaborations, and I mean, the funding is always a challenge, you know. So there are definitely, I mean, we are trying our best, at least for the students to always find the possibilities, and early career researchers that they can travel, do their research visits and so on. But the funding is really a big barrier, so many countries are struggling with, in Africa, are struggling with the funding to send students, staff members, even for attending the meetings. And then if it is a longer period, for like research visits, and then if you constantly ask for the funding abroad, well, there are also many limitations. So we are trying our best. I think we are managing with the students to actually give them the exposure to the international community and collaborations, but definitely it's a barrier. I do think that I mean, there is, as Solomon mentioned, there is currently, you remember what I mentioned yesterday, that one of the primarily challenges is that many countries are starting from scratch. When you are starting from scratch, from zero, with all the development, starting from institutional, human capacity building, infrastructure development, and so on, with a very limited resources, human resources, beside all others, funding and so on, it is, of course, a big challenge, So very often we come here, we get different ideas, we see, oh, there are so many possibilities to interact and collaborate if we get in touch and so on. Then we get back to our day-to-day reality when you are merged in so many things and you don't even have time to actually get back and start one more thing, So please, I mean, here, I think this kind of meetings that brings people together, I mean, if we are motivated to do something, it should be like from all different sides, So if we don't get in touch, please get in touch. And if you have funding to like come to Ethiopia, Morocco, any part of Egypt, Uganda, any part of Africa to give trainings like our colleague from the LSSD said, it's not a problem. If we don't approach you, please approach us, because definitely the needs are there. And I think, if the funding is there, somehow available, I mean, there are more than enough needs to actually cover it. And then I think that with the portal, we will take a note for speeding it up so that we can include not only in terms of the collaborations, but also trainings, which was the idea initially. Yeah.
If I can just say, just follow up on some of this, that within the African Astronomical Society, although the funding is limited, we've had programs for supporting early career researchers through grants on an annual basis, also for PhD prizes. And so we're doing our best to sort of address these shortfalls. Of course, it's demanding from a financial point of view. And this is where I would say that the example here for the IAU, where there's been significant amount of money that has come from benefactors to support attendance at the IAU of African astronomers, and particularly early career and students from all over Africa, who otherwise would not be here at this meeting. We were so grateful. We're so thankful to these foundations that have done that. But if they could see their way to continue that, not just see this as the end of, in a week's time at the end of this meeting, that's it. We want a legacy, as Kevin Govender has said in his remarks yesterday. So, there's big challenges for us, and we're willing, we're trying our best, but I think we would very much value support from the international community.
So given that you mentioned publishing, it is very well recognized in the policy sphere that there are some issues with it, and that in particular the transitioning of journals to an APC model might not be the right way forward. And if you're interested in that topic, I've actually suggested an unconference session on the future of scholarly communication. If you're interested, look at the details on Slack, and Vanessa McBride has actually added a recent scoping paper from the International Science Council on that. That is really well worth a read.
You want to comment on that? On a different topic.
Yeah, so just have another comment about. I want to raise one of the proposition, one of the suggestions that David has proposed in IFS. I think is also previously. So is to make talking about the ground-based optical telescopes. So the idea is just to have a platform network when we can have all the telescopes in Africa. So I'm not sure how far we can go with that one.
Well, yeah, I spoke about that in my talk this morning. So, yeah, we have this program called the African Integrated Observation System, which is designed just to do that, including, of course, your own country in Morocco. And I'm really optimistic because, you know, I've had we've had positive feedback from all of the people, main players in the observatories so far. So, you know, this is definitely something that we're going to take forward over the next year or two. And I think, you know, it's very promising.
Yeah, kind of related to that. We've heard of a few places where the plans for new observatories and so on. And are there ways that these observatories can, you know, have that in mind from the start, sort of build in the plans to be part of a wider Pan-African network, you know, from the ground up, and not have to think about, okay, how do we join that and re-engineer it afterwards?
Since nobody else is raising a hand, I will just bring another topic. This has been asked. Oh, you want to comment on that?
No, I want to talk about also to focus about the engineering capabilities of the astronomical community.
Okay, go ahead.
Because actually you don't have much of experience related to engineering, astronomical engineering in particular. Especially we have a very advanced instrument in Egypt called the KFS, قطامية Faint Object Spectropolarimeter. And we had a problem related to optics in this instrument, and we have the company told us that the instrument is working very well, and we are putting stuck, and the instrument had problems related to optics. Then we were unable to know what's the problem of the instrument, and then after that, we asked this company to repair the problem, and then they have a new focal reducer instead of the previous one that we was convinced us that it was working very well. So I want to focus about this optical engineering and to foster these jobs in Africa in order to have some people working in this field of specialization. And also we are going to build our new large optical telescope, Egyptian large optical telescope, and we need a lot of experience related to engineering. And we need to know about the how to build our telescope and how to assign the optical parameters of the telescope, and which instruments that we have to do or to have to use in our telescope. We need the help of all African communities or astronomical communities all over the world to assign the best parameters of the telescope, our future telescope, because it's very important actually, and we don't have much experience related to this.
Does anybody want to comment about that?
Yes, there's a small comment from me. Yes, I think we already started discussion about how to build and how to put a big telescope in Africa, and where and how and for what science behind this telescope we need to do. It's clear that if we want to have a big project, you must follow the experience already done by Europe and elsewhere in the world to set up a regional projects, big projects, not only national projects. There is projects everywhere. In Morocco, we have 2 meter projects to build to set up 2-meter telescope in Egypt, 6 meter, and also perhaps other projects. But we need to put hands together to build a big project and make it regional and not national. And I think this is what it's behind this focus meeting. It's to discuss about that, to take a right decision before starting to spend a lot of money for projects we don't achieve in an optimal way. I think that to do that, the best platform we have is AFAS now, African Astronomical Society, and we need in AFAS to take on hand seriously this problem of a lot of small projects and a lot of telescope everywhere and don't working. I think we need effort in this area. Thank you.
Okay, maybe I can ask the panel to just give some concluding remarks so that we can close the session and the focus meeting, because we are running out of time now. So if you would like to just go in order, just final word, just 1 minute.
Maybe I have to finish this session or the focus meeting, but also we didn't mention anything about radio astronomy. It is very important also for Africa, and we are all willing to have radio telescopes in our African countries. And we have a meeting in the other room in this afternoon, and I asked the African Astronomical Society to adopt some things that can talk to African Space Agency to adopt this action in order to have some radio telescopes inside the other African countries other than South Africa, of course, and maybe they can have support in this point. And finally, I want to thank all of our scientific organizing committee for their help, and I started this focus meeting as an idea about the Egyptian Large Optical Telescope, and then it being bigger and bigger until we included all optical and dark skies in all Africa continent. So I want to thank all of them, and want to thank all of the invited speakers that attended this focus meeting and make it successful, like we have seen today and yesterday. And I hope we can continue our cooperation and continue our plan to be sustainable and in order to implement what we have reached in our focus meeting goals. Thank you very much.
And I'd just like to add, I'd like to thank everyone in this room and everyone who's been in all of these 6 sessions these last 2 days. Just seeing the room with, you know, a lot of people here, it shows that, you know, it's being supported. So thanks.
Okay, let's give a big applause to the whole participants and to the scientific organizing committee of this session.
Maybe we can take just 3 minutes to take a
picture.
Yes,
I think there is something in the program now, right? The business session is open, or is?
I don't know if that's open.
Does anybody know whether the business session is open or is it closed? Is sitting? Okay, we will arrive late otherwise.